In the afternoon, we are having a workshop. It's called the Weekly Supervised Computer Vision Workshop. And I'm very happy to start that workshop, finally. For me also, finally, in DABA Deep Learning 2022. It has been 3 years that it's in the process with everything going on. So it should have been starting 3 years ago. So I won't go long with the introduction. I just want to give a 30-second introduction about why weekly supervised learning. And I could say also why computer vision also, especially in that room. I know that the African community is very interested by NLP, and there is a lot of excitement towards MLP, and computer vision is very less visible here in the continent. And by the way, at the same time, we have another NLP workshop. So we have the competitors. So computer vision is very important. You can also think of images as being language without words, right? So that's another way of seeing, and often images are universals, right? Everybody on Earth recognize the human, they recognize the landscape, they recognize object. That's something that is shared among all humans from all the culture, and that's something very powerful to connect the people. So I think I really encourage all of you to also work in computer vision and not only language, although language is super important. And another thing I could say to join the two is that in the last years, and you have heard about it in some of the plenary talks, there has been the emergence and the increase of the vision language model. And that's a model that learn jointly the image and the text, and that learn a shared embedding. And that's something also that is moving forward. And by the way, the first speaker I know has some work in that area. And finally, why weekly supervised? There are many reasons to justify the need of going towards weak supervision. Some people would call it unsupervision. But one of the two reasons, the first reason you can think of is annotation is very, very costly, right? Just to say, in some of the presentation you've heard about semantic segmentation, roughly it takes about an hour and a half to annotate a 2D image, just one 2D image, right? And now we train on thousands or millions of images, so you can guess about the cost. And the second thing, if you think about, for example, 3D takes about almost 5 hours for a hectare of 3D data, so 100 meter per 100 meter of 3D data. So it's really, really costly. And if we reduce this cost of annotation, then we need to go towards weekly supervised. And the other reason is more fundamental. Some of the conditions that appear in the world are just rare events, right? There are conditions that are not often observed. For example, if you want to handle a very heavy snow, you need to you will very unlikely have many recording of severe snow or even hail or shooting stars or everything like that. So at some point we need to move towards something that is learning with only a few examples, and that's the topic of the workshop. And I'm very excited. There are many good speakers that will be on stage showing you exciting work. And just to say to all of you, the workshop is also being broadcasted and recorded, so you will have access to the recording, and everything will be on the website after. So that's all for the introduction. Just a quick thank you for the organizer that you can see here, several colleagues from INRIA, Value AI, or University of Tübingen, and 2 volunteers here. The one circled in white, or the one on here, actually in Tunis. And so don't hesitate to come talking to us after. And this is the program and the agenda of our workshop. So we have 6 speakers that are here. 4 of them are on site, and they come from different backgrounds. You have people from academia, people from industry, and you will see a variety of work and research. And again, 4 of them are on site that you can don't hesitate to come and discuss with them. And there will be a coffee break and a poster session during the 2. That's all for the global introduction. So the first speaker is Mathieu Cord. To say a few words, Mathieu Cord is a full professor at Sorbonne University. He's also the principal scientist at Valeo AI, and that is an artificial intelligence research company in France. A notable thing, he received a chair on artificial intelligence for visual reasoning in deep learning in 2019, and he has a huge list of papers, among which some papers on domain adaptation, visual understanding, uncertainty estimation, GANs. And notably also, I know that he's going to talk about transformers. He has some very early works on vision transformer that were very highly visible. And by early works in vision transformer, we're talking about 2021, right? It's very, very recent, but it's still among the very early work. And since I know that he's a big fan of cooking, I let him, the floor is yours, and I let you cook a nice presentation.
Thank you very much, Raoul, for this nice introduction, and thank you very much for the invitation. So thank you again, Raoul, for the invitation. So I'm going to talk about vision transformer today, and so yeah, just one thing about the affiliation. So I am in Sorbonne University, and in Sorbonne University we do have a Sorbonne Center for Artificial Intelligence, and this center has also an antenna in Abu Dhabi. So it could be interesting for interaction with there also for you. Transformer that's true, is a very recent kind of deep architecture that have been introduced first for NLP, natural language processing, but then people have developed some adaptation of this kind of technology for vision and visual application, and I'm going to talk about that today. But first, let me come back earlier and to see, what's going on in the last decade. And so what we have seen really is like a big version, like a kind of renew in artificial intelligence with the neural network, and in particular in vision was one of the main field where this kind of deep neural net was very very successful, and typically like the star was really like convolutional neural net for let's say the big challenge that at this time was about the kind of ImageNet challenge, that is a classification challenge in image with 1K label at the end. So you have this kind of input that is one image, and at the end you have to decide among 1,000 of classes which one is the good one for the image, and in between you have this kind of deep neural net that is convolutional based. I will come back to that, but this just to say that for let's say 10 years there were a huge amount of development, simplification or complexification of this kind of architecture in order to be able to process any kind of vision-based application, right? And so one of the questions is that is it going how the things are going for the next decade, and typically we can say that transformers started to be a real a concurrent for the ConvNet at this place, right? And this was, as I said previously, introduced, so in 2017 for NLP purpose, but then we are people from the community developing now some kind of new things for vision with very good result I'm going to explain. Okay, so This is in terms of architecture, but the things are going also when we are talking about machine learning things. There is the, let's say, the architecture, algorithm, optimization, etc. But also, of course, the main things is underlying things is data. Okay, and so here it's, I mean, that was because we developed the ImageNet dataset. That is a huge dataset at this time, with about 1 million, more than 1 million images labeled, okay, and very accurately labeled, okay. That makes possible to develop this kind of system, okay. And so it's about 1 million data, okay, fully supervised, annotated, as Raoul explained. I mean, like, it takes times. Of course, this is for classification. It's less time consuming than for segmentation, but okay, it's still a lot of time to do that. And so one of the questions for the next decade is that can we get rid of any kind of annotation? And in particular, I mean, one of the questions of this very large vision and language, typically, I will come back to that at the end of my talk, combination, us to have this kind of fully unsupervised things, and typically just going through scraping the internet and get some kind of pairs of images plus caption, textual caption, or things like that. Okay, and can we do, I mean, all the stuff with only this kind of things? Okay. So it's a kind of bit by I would say that certainly, I mean, like in the coming years, we will see much more about this transformer and this kind of fully unsupervised coming from internet or other kind of pretext task to do the job. Okay. All right, and if we come back even before, just to see, for instance, the interest of this kind of connect architecture among against the things that was done before, we can say in the previous decades, so in the 20th, I mean, the demand and for 10 years, people was really, I mean, like, researcher occupied to develop this kind of very nice pipeline for classification, image classification, and the thing that is interesting is that part of this part and typically the early step of this processing was done by handcrafted operation or filtering or things like that. So that means, like, typically local gradient extraction, coding, and pooling, orientation. So all things was defined by hand and then projected with unsupervised visual code to get a big image signature. And then we did have like a very classical classifier that can be typically at this time the support vector machine classification for that. Okay. And so starting from that, when we see, I mean, the relationship with the deep learning, what we can see is that there are some similarity, of course, in between them, but also some differences. And I would say that one of the main differences, of course, is the depth. That means that with deep learning architecture like this one, you will have much more step in between, I mean, like the input and the output, of course. And the other things that is very important is that there are some similarity in the way that you extract some intermediate features, okay? But the main things is that here, everything is done with parameters, and these parameters are learned during the end-to-end learning of the whole architecture. Okay, and that was certainly one of the main difference, and that make a big difference also in terms of accuracy. I mean, like on the capacity of the system to work much better than this one. Okay, was really, I mean, like, because everything except the kind of architecture was learned here, right? Okay, and not designed by hand as we had before, right? Okay, so one of the questions today is that what is not in this kind of very deep convolutional neural net, and for sure, and people was thinking, of course, of how to integrate a more global attention and things like that into the convolutional neural net. But finally, at the end, I mean, one of the most elegant solution emerge with the transformer. Okay, so just to start with that and to see what is the attention and where is the attention in the previous architecture, so the convolutional based architecture. Of course, we did have some kind of in this kind of architecture, you know, you go through the image with somehow some kind of small filters, let's say 3 by 3. Okay, and so that means that one intermediate output is depending on somehow, you know, a neighborhood around one point that you have into the input. Okay, so you do have this kind of local attention. Okay, but it's only locally. If we talk about attention, just saying that, okay, we need to have the information to be able to compute the intermediate output that you have here. Okay, so coarsely speaking, and you see with this kind of a very coarse picture, but just to explain the idea, okay, if it's locally, I mean, like the attention, I mean, so the way that you are going to compute an information for one of the patch here, okay, one of the patches here, we just depend also on the information and locally around here. Okay, but if you do have this kind of global attention that you want that the way that you are going to compute a feature for one patch here will depend on all the other patch, and in that sense, it started to be a global attention, right? So you can see how the global attention may be computed in this kind of self-attention that you can have for one image, okay, for all the different patches of the image, as this kind of attention map that you see here. Okay, and so one of the question is can we do this kind of thing? So can we compute this kind of global attention that we don't have in the ConvNet, and how we can do that? Okay, so this kind of things come from let's say natural language processing development, and in particular for machine translation. I mean, they were thinking about this kind of attention, and they were very interesting in building these kind of things that you can have if you take, for instance, 2 sentences. So you have one sentence in French, for instance, here, and what kind of possible traduction here, and you want to be able to have this kind of weight in between any kind of word that you have here and all the words that could be interesting and making sense in the translation. Okay, and so for doing that, this kind of attention process so I'm going to give a very broad introduction about how they did that for the translation, language translation models. Okay, they do have this kind of encoder for the first language. So here you are in the French, you have the seconds, and so you go through the kind of encoder, and you pass the information here at the end, and you have the kind of decoder to be able to start and to find actually the right sentence at the output in the other language. Okay, and what people try to do is to learn, of course, all the parameters together that they do have in this kind of things. Okay, and so if you think just not about the model, we don't care about the model here, but how the attention is from one language. And for each of the words of the first language for the second language, what you see is that all the information is just at the end, here, at the end of the integration of all the information from the first language. Okay, so if you want to take into account of all the representation of the different, let's say, word representation that we are going to talk about token now, okay? So for each of the token here, of course, you can take all this token and to have like this kind of sum. It could be at least better to take into account of the whole word from the first language, okay? And what people after realize that it could be even better if you are able to propagate this kind of information, not only at the beginning of the decoding, but for all the steps of the decoding, okay? And so you can have these kind of things. And of course, certainly one of the really, I mean, like a very close solution proposed just before the transformer, but the basic idea is here, is to be able to adapt this for each step, to be able to compute an exact and dedicated attention for each step. And that can be different from one step to the other step. It's not the same, okay? And it depends, because it depends on where the decoding step is into the process, okay? And so when you see this kind of extension of the basic way to transfer attention from one language to another, what you see is that at each time of the process, okay, when you decode, you are able to compute these kind of things, okay? And so this is really, I mean, like the kind of things that have been transferred and developed, of course, in the transformer architecture. Okay, so the transformer architecture I was mentioning was published in RIPS. Okay, so 5 years ago. This is the big picture to do that, but it's exactly the same idea of encoder decoder for translation was there. Okay. And except that the way that you encode is a little bit different, but you still have as many tokens as you have, let's say, words in the first sentence. And the connection with decoding is that for each of these features are going to cross attention for any tokens of the decoder. Okay, so this is expressed in another way here. I mean, you have the encoder and you go through this kind of attention and cross attention over the decoder that is here. Okay, so it can be done in the cross attention process that you have here, or of course, and this is very interesting also, and in particular for image classification, you can do not cross attention, but the self attention. It is exactly the same process, except that the attention is done on the same sentence. Okay, so typically, if you want to move from the token input to be able to compute a more abstract representation, you are going to do a self-attention of any token with the other token of the same sentence, and you are able to repeat this kind of things, for instance, n times here, and you are going to have a very useful self-attention representation. Okay, so okay, that's cool, and to give just an idea of what is inside this attention process. So when we are talking here about doing attention, okay, how we compute this attention. And again, this is very simple in this transformer representation. Okay, so you do remember you do have this kind of word tokens, for instance, at the encoder level, and also the decoder level. You have also tokens. So and the idea is to be able to compute every point in this map, okay, that give you typically the attention that you can have from one word from the encoder with any word of the decoder. Okay, and this is done like that. So this is the main way and the main proposition of Rashani and colleagues to do that. This is, you take as a query any word of the decoder that you see here. Okay, you do have a projection here, right? Okay, so there are parameters here, and then in that space you are going to do the same kind of thing. So another projection as key here, represented here for any for all the words from the encoder tokens. Okay, and then you are able just to put somehow a dot product between this query vector and any of them, and just of course with this kind of softmax and normalization, you are going to have like exactly the score of the map for every token in the query, okay? And from this mapping, typically you can compute an output for this query coming from the value projection that you can obtain also from the other token, and then you can combine all them together, and you have a new vector for this query, okay? So this is a very, very simple process to do the attention in language, in natural language processing. And typically, so the last question is how we can adapt this for image classification, and I will see later how to do for other kind of task for in vision, okay? So if we start with that, what we can see here is very clear is that this is for NLP, and if we want to do it for vision, okay, visual patterns, okay, the only thing that we need is to, of course, to have visual patterns, okay, so patches, okay, so we have to represent at one part of the modeling of our visual information, we have to divide and to be able to represent the visual information as visual patches, okay? And as soon as we do have that, we can do exactly as we have had before, and I had explained before, okay? So finally, if I start from one image and I want to do like classification, so several layers of transformation, deep transformation, instead of doing convolution, and I want to have like this kind of global attention inside my process, okay, I can do it as soon as I'm able to see my image as a set of tokens, right? Okay, and so this have been proposed last year, and I clear that was the first paper to successfully, I mean, like doing that for large image classification challenge. Okay, and so from that and this kind of transformer encoder, exactly as you do for a natural language processing, so you can repeat all the things. I'm going to give more detail after, but okay, then at the top of that, you just get, so you can do a sum pooling, or you can just add a very special tokens and use this token to go through the final representation and the output where you need to classify the image. Okay. All right, and just to say, yes, a little bit more detail about the transformer encoder. This is exactly this kind of things actually that we have in image, is that you repeat L times. So you have L times this kind of transformation. So you can imagine that it can be quite deep also, of course. And typically from this patches, okay, that you have, and you have a first projection, so you have to split the image. So let's say 16 by 16 as proposed in the first paper, and then you do have the projection, and so you have vectors, and from that vector you go through the normalization, attention block, exactly as I presented, okay? And so everything is done in residual, and so that means that you add with the initial things, okay? You do also have this kind of normalization step that is very classical in image processing, and you alter, you do have an mix in between the attention and, of course, MLP or layer, classical neural net that you have for fully connected, I mean, but at the patch level. Okay, all right, and this is done, and thanks to that, I mean, what they really show, and that was the first time, and it was very impressive result, is that they were able to, in this initial VIT paper, they were able to even to beat, I mean, like some of the most recent convolutional based system for the ImageNet. So when we want to see on ImageNet competition, what are the scores? So in general, it's the accuracy. So higher is better. And then on this competition, it's a top one. I mean, like 80 is a very good score. Okay. And so the only thing that was not cool with the first VIT paper was that they need to pre-train on a huge data set, let's say 300 millions of images. That it was a paper from Google, so it's a private Google data set. So it was not available. It was not a solution available for everyone. Okay, and so what we did in this a few months later for a web paper is that if you pay attention about the way that you do the learning, okay, everything's into the learning, you can do as well as them, or even better, without this kind of big pre-train. Okay, so that was something that we published in what we call the DIT paper last year in ICML. And what you see is that with this kind of things, you can go really, I mean, like full close to state of the art at the time of publication on that data set. Okay. And there are a lot of extensions that you can do for this kind of things. Of course, one of the first questions, and this is very important for computer vision guys, is that how we can choose the way that we split the images. So the first operation to transform the image in a sequence of patches is crucial, is very important. And of course, there are a lot of open question on that. But typically one of the bottleneck for the transformer is that the complexity of the attention process is quadratic with the number of tokens. So of course, if you split the image in a lot of small blocks, okay, you are going to have the complexity that is going to grow quadratically with this number of tokens, right? So it can be a problem, and there have been proposed a lot by colleagues, a lot of solutions to handle these kind of things. And one of the things is this is very classical also in computer vision field is trying to have a kind of hierarchical processing. So not to process all the attention and all the block all together at the whole level, but trying to do some part of locally, okay, and then to make them together and then to go through a more global process, okay. But of course, this is a limitation, as I said at the beginning, because we really wanted to go through this global attention as soon as possible and that was the way that we want to differentiate from the classical convolutional based system. Okay, right. So where we are at the moment, I just explained how we can adapt from NLP transformer techniques to vision and to vision for classification. So one of the questions could be now how we can do this kind of things for other kind of task, not only classification. And in particular, if you remember in the translation things for NLP, they were a decoder, okay? And so we can find also the same kind of idea that can also be adapted for vision tasks like detection, segmentation, continual learning, many things like that, right? And so to do that, there are very interesting architecture that have been recently introduced by colleagues from DeepMind. That is Perceiver IO, and this is structured like that. So as I said before, you transform your image in just a set of tokens, and there is here a first projection just to limit the number of tokens, but we don't care. You can say that this is more or less what I just explained before. And what is changing is the output. So it's what you see here. And the idea is that up to now, here I just have a classification and it's over. So just one K vector. But if you want to do more complex things, you can think about decoding from this information that have been, yes, really, I mean, the latent information coming from the data, from the input, okay? And you want to recombine this latent information, okay, that should contain all the useful information from the image for the task, okay? And this task, depending on the task, may have different shape, and in particular in terms of output query and structure. Okay, so let me show you, for instance, one example is that's completely like that. This is the detail system. If you want to do detection, what you can do is, okay, you do have this kind of representation for all the image, and you are going to combine and again with a kind of attention process that is always the Q K V process that you have here. Okay, you just have to define a fixed number of boxes that you are able to detect into the image. And for each of these boxes, okay, you go through the decoding process. So what you can observe in the image, and then the output, for instance, for the red one is one box plus the content, I mean, like the class of this box. Okay, so for instance, here you have 4 boxes. So this is fixed at the beginning. You learn this kind of system to recognize, I mean, the correct box. And when you have to process a new image, all right, you come with all these boxes, and here the output will tell you, okay, I find one box here, and this is the bird. The second box, I do not find anything. For the third box, I find another bird in here. And the final one, for the fourth one, I didn't find anything. Okay, so the output could be like that. And of course, if you have one image with 4 cards, you will be able to find the 4 different cards, etc., etc. Okay, so this is a very simple change of the global architecture, but this is coming at the decoder level. Okay, the same for segmentation, for instance. Okay, you don't have to do a much dramatic or change in terms of global architecture. You can keep more or less the same kind of things for all the feed-forward process, but except the decoder, you will change the output query array. That will be certainly, I mean, like one query array for 1 pixel or for one block of pixel, and then you are able to do for each of them exactly as I presented before, except that for each point, each query array here, you don't have any more, I mean, like one box with a class, but you have 1 pixel with a class or 1 pixel block with a class. Okay. So there are, okay, I'm going to switch that. So there are many ways to, I mean, like to adapt this kind of big architecture and big process, very general big processing architecture. And you can do also, of course, continual learning, not present into the detail and these kind of things. And you can extend, I want to keep time for question, for video. Raoul, can you tell me how
yes, you have a few more minutes. Let's say 5 minutes top.
Yes, good. Okay, I will try. Okay, so okay, and yes, typically a last extension that is important is that you can also change the input. So if you want to consider no more, let's say 1 image, but for instance here, and for automotive, let's say autonomous driving purposes, for instance, it's very interesting. So you can have, like, let's say 6 cameras instead of 1, and you can do exactly the same thing as I presented before at the input, except that you will have, of course, more tokens, but this is the only change that you are going to have. You do the projection and the processing is the same. And if typically you want to have like an output that could be like what we call the bird eye view representation, let's say what is the 3D scene and how we can see the 3D real scene of that. Where are you going to manage this? Of course, again, at the output level. And so you just change the way that you want to represent the output, and the output will be like that. And you can get a above representation, for instance, here, a binary representation with car, not car, everywhere in the bed, all right? So very interesting. So just to say, to summarize on the vision transformer, global attention, very interesting. Competitive architecture that we have now at the best level of the best competition. We can beat really, I mean, like with the ConvNet. And there are this very nice, I do like this nice fusion or merging, and with also with the attention, with the mixing attention process that we can develop with very, I mean, like easily in this kind of architecture. That is not the case, I think, so for ConvNet architecture. And of course, yeah, there are many questions on how we can go through more universal representation. But let me finish this talk on one word about mixing visual and language models. And I think this, of course, could be interesting also thanks to the purpose of the workshop on weakly supervised. And typically, one way to do the stuff of weakly supervised is to pre-train a very nice model and then to adapt with a very few extra learning data, or even sometimes I'm going to show you the example, of course, with the click model here with zero new data as learning. So it's a kind of zero shot adaptation, so direct transfer that you can do with many of this kind of model. Okay, so how it works, this is only, I mean, like the difference with what we have seen before, as I said, with ImageNet, is that we are no more learning with the one image and one class for each image, but now it's one caption for each image, and this caption are coming with a huge number of errors that have been done from the internet. Okay, so for each of them, you have like the good correspondence, and the otherwise are bad correspondence. So from the first image, and the other sometimes are not good typically, and we can learn these kind of things in a contrastive learning. And once it's learned, the idea is to reuse, I mean, like this kind of pre-train a very big image encoder that we have here, for instance, to be able to do classification. Okay, and of course the text encoder have been learned also. And so how you can do, for instance, ImageNet classification, but you just say, okay, this image, it's a photo of, and you put the first the first class. Okay, so it's a photo of a plane, and you will have a score. And after you do, okay, the same image, it's a photo of a car, it's a photo of dog, etc., and you will select the more similar things, and it's over. Zero shot classified. Okay. So this is very interesting, and this has been derived in many ways for end-to-end vision and language transformer. Okay, also because the image encoder, of course, could be a ConvNet or could be a transformer, and of course the most recent things have been done with transformer also, because at the text level we do have transformer things also. Okay. And then from that, you can adapt to reasonably other kind of data set with several tasks. And in particular, you can, and there are a lot of experiment at the moment with to see how this system perform for what we call complex visual scene understanding. So there are several downstream tasks where you take your system, you pre-train, you fine-tune over the reasonable data set, and then you test on this kind of things. Okay, and so this kind of visual language model are really, I mean, like close to what people call foundation models, and typically, I mean, like in the research center of Stanford for doing that. And this is, I mean, really the idea is, can we get, I mean, all the information from a pre-trained huge GPT-3 plus VIT, big VIT in vision. I mean, like to develop a lot of downstream tasks for. So it can be 0 shot, or it could be only few shot, or it can be just fine-tuning on a very small and reasonable training data set. Okay. So last slide. Yeah. Okay. Just to sum up, so I would say that as I said in my introduction, I mean, like ConvNet was really, I mean, like the best, and for 10 years, by the community, I mean, like to be able to improve the result, of course, on ImageNet, and to do everything with that we can do with convolutional things. And certainly we try to do the same kind of development and understanding and combination, of course, with ConvNet, with Transformer, and in this decade. And one thing that I so mentioned in blue is that certainly, I mean, like what is changing is the order, I mean, like of the size of the data for at least the pre-training that we have for this kind of things. That is, let's say, 1 million of images for the ConvNet, and something like 1 billion of images for the one that we are considering now. Okay, so I'm going to stop here just to keep time for question and interaction.
Thank you, Mathieu.
Thank you very much.
Thank you, Mathieu. Thank you very much for the talk. Very interesting. If anyone has questions, just raise hand. There's one there.
Yeah. Hello.
Okay.
Hello.
Hello.
I don't know if you can see Mathieu, but I'm trying to
More or less, but
show
okay.
with the camera. Okay.
I see something. I see something.
Yeah, hello. Thanks for the lecture. So I'm still new to the idea of transformer. So this question is very basic. For classification tags, do you need the full encoder decoder side of the transformer? Can't you just use the encoder side? Did you get it? Hello?
Did you hear the question?
I'm here, but can you repeat the question because the connection?
A bit closer, the microphone.
It's
on. It's on. Yeah, it's on. Just a bit closer to you.
Okay. Yeah. So I was saying for classification tags,
yeah.
do you need the encoder and the decoder side of a transformer, or will the encoder side be enough?
Okay.
Or does the decoder side provide extra information that is needed?
Yeah. Okay. Okay. Actually, you can. Yeah. Let me come back to the. Yeah. I can see. So you can limit, I mean, the things to the encoder. Okay. So because what you really need to have, like for the classification, what is the most important things is the self-attention process. So you do it. It's exactly what you do in the encoder way. Okay, but you still have the question is that at the top of the encoder, okay, you can have a representation, latent representation for each of the token that you have at the beginning, at the input. Okay, so you can say that this kind of rich representation of every part of your image. Okay, and so for classification, usually what people do at this time is that you just do a pooling. Okay, that's exactly what we did also with the classical ConvNet things. You do a pooling to have only one vector, and you go through a last layer of transformation to go through the output. Okay, that is composed of a vector of the number of classes. But okay, what usually, I mean, like people started to do before is exactly as for NLP, is that you can consider also an extra token at the beginning. Okay, and this extra token is completely learned, so or can be defined by different way. But let's say you can imagine that this is a random things at the beginning, and you can learn it, but it is going through the process. Okay, and so with the attention with all the other through the whole process of L layers. Okay, and so that means that on top of that, this usually called class token contains many information on all the necessary information coming from the image. And this is the only one that is used for the last layer, fully connected up to the classification. Okay. So there is, and you can say eventually if you want that this is the decoder is this last layer for that one, but it's let's say that in that case there is no really a decoding stuff. Okay, is it answering to your question?
Yes, yes, he said yes. So there is another question. Yes, go on.
Yes, hello. I have a question about the swing transformer. I didn't get very well how it works. The swing transformer.
Yeah, sure. Okay, so I was talking about the swing transformer just to explain one of the problems that we have with the vision transformer. That is a very important one. This is a own question for people in computer vision, is that, I mean, like people from text or people from other kind of media processing. I mean, and in particular from the one that is 1D processing. I mean, like to transform one image into a sequence of something. Okay, and so what we have seen during the past is that it's not very easy to do that because of the natural topology of the image that is 2D. I mean, like, and so the way that you are going to pass through the image to transform this into only one sequence or one set of things, it could be very dramatic for the rest of the processing. Okay, here for the transformer, what is good is that the attention is going through all the tokens. And typically in the first thing, the idea was, okay, I take the image and I split the image in 16 by 16 tokens. Okay. By doing this, I mean, like you have, this is a certain way, I mean, to see the image in terms of resolution, for instance. Okay. So that means that inside these things, I will not have any detail. I will only have one vector for each of them. Okay. So I have no more visual information or things like that. I mean, like 2D information inside of this. Okay, and so sometimes, I mean, we can prefer to have something that is finer. So it's not 16 by 16, but something where we can have more resolution here. Okay. Just do we do a more fine splitting as the one that is done here, for instance. And if we take all the token here and we just do the attention, the complexity will be quite high, okay? Because it will grow quadratically with the number of tokens, okay? So what they propose here in this swing transformer is say, okay, I give up the global attention at the first level. I try to do exactly local attention on these different patches. Okay, so you have, it's like if at this layer you have like the attention-based process, but you don't want to have an attention for this block with one of this block here. Okay, inside this super block here. And so you are going just to step by step going through this kind of less finer block, and then here at this layer you come back to something reasonable and you can do a global attention. Okay, this is the only things that they change.
Thank you.
Other question in the back is coming up.
Okay. Hi. So my question is regarding the first stage where you're creating the patches. Now, I'm thinking about in medical images where most of the time the biomarkers are sort of like tiny patches, right? And this would probably result into having a lot of patches that are uninformative, right? So is there sort of like an efficient way to select the informative patches on an image before passing it to the to the architecture?
Okay. Yes, thank you for the question. I mean, there are many works that try to do this kind of things. Not for certainly, but okay, I'm not aware about ones that do it typically just to keep informative and non-informative, but people try to at least to say, I want to select not all the tokens, but try to select a subsample of the tokens for the complexity equation, for sure. Okay, so because of this quadratic complexity. So if you have a way, I mean, to select and to remove some of the tokens, because certainly, I mean, like it's information less, you can at least become become competitive in terms of complexity. Okay, so just before doing something that could be interesting and more interesting for let's say, for instance, for your medical studies, the first question of selecting some of the tokens and not considering all the tokens is already coming, just to be able to process the things in with the transformer. Another way to answer is also to say that you can have this problem as soon as when you want to process small images, and you still want to have this kind of split, because you want to have several tokens. You don't want to have, let's say, only 4x4 tokens. Okay, and so if you have a small image, then you need to have then small patches, and these patches are less informative. So that's true for sure. Okay. But I would say that in that case, I mean, what people do is try to, I mean, like to have this kind of during the learning, I mean, like the transformer architecture, get rid of this kind of patching. So by the there is no specific, but certainly it could be interesting. I don't know if people already did some experiment for having this kind of let's say, useful or meaningful patches information selection. It could be interesting.
Maybe last question is someone wants. Still one? Yeah, okay. Last one, maybe Umberto, you can.
So thank you for your presentation. So I have a question about the comparison between transformers and CNNs. So can you give insight about why transformer worked better than CNN, and in which problem? So can you just give some type of problem where we will recommend a transformer and some type where we recommend CNNs?
Good. So as I said, for me, one of the main at the beginning, one of the main difference is coming from this attention process that is global. The transformer, and this is not the case for the CNN. I mean, step by step. Again, at the end of the day, of course, in convolutional neural net, I mean, when you are at the 15 layer and you see one pixel at this layer, of course, coming back for the different layer before, you see that the field of view for that this kind of intermediate output is not very local, but step by step in the transformation, this is local. Okay, so for sure, as soon as you do have a problem where it makes sense to have or to take into account of the relationship between something, let's say top left and bottom right, okay, you would expect to have a better solution with transformer-based deep architecture for that. Okay, so for instance, if you have complex images, large images with different objects, but it makes sense to have this kind of relationship that can emerge or that can be taken into account. I would say that transformers certainly is a good option for that. Okay. Yeah, the other point for transformer that I think is interesting is that when you really want to interleave vision and language, and typically, I mean, like if you are thinking about internet web page analysis and you want to learn from that, okay, what people try to do now is to say, okay, I do have like one sentence, two sentences, so a set of text token, and then I have an image, and so it makes sense to represent the image in the same kind of representation as before. So again, like a token, because in that way you have like a universal representation of everything as tokens. Okay, so typically for web page analysis, and so the kind of language and vision things, I think for this question of universal way to represent the things, and so a more straightforward way to compute them, image, one video token, also text, etc., just a set of tokens, it would be better. Okay. Otherwise, as soon as you dependency is enough and you have let's say a specific problem, you don't have, for instance, huge data set, and it makes sense to just grab this kind of local things with good filters and so on. I think, yeah, ConvNet is still very good things.
Thank you.
Okay, thank you very much. Let's give a round of applause to Mathieu also.
Thank you very much. It was my pleasure.
Thank you very much, Mathieu, for this. And we're going to move to the next speaker. So the next speaker is Umberto Michieli. Umberto Michieli is a senior researcher at Samsung Research in United Kingdom. He got his PhD in 2021 from the University of Padova, that is in Italy, right? Yes. I'm still okay. And among others, he has also done, for example, a visiting PhD research in the Technical University of Dresden, so Italy, Germany that time. And he has work and interest towards continual learning, in domain adaptation and federated learning, right?
Yeah, that's correct.
So that time the floor is yours. Sorry for that.
All right, no worries. Okay, so yeah, I'd like to start by thanking the organizer, Raoul, Fabio, for these amazing events, all the other organizers that are behind the scenes, and the volunteers. It's really a pleasure to be here today. And I'd like to get started really straight away. So today's talk is going to be about learning to segment images with limited data across domains, devices, and tasks. And I will explain what does it mean in a second. Maybe can we click on the presentation, because this doesn't really work. All right. Okay, now it's much better. All right, so let me start from few words on the motivation. And I bet all of us know what semantic segmentation is, but just to be sure to be on the same boat, same boat. We want to basically label an image at a pixel level. So it's a dense predictive task. And also in this case, the deep learning revolutionized the field a few years ago. And it finds really many applications in the real world, such as biomedical imaging, autonomous vehicles, and so on and so forth. However, unfortunately, in order to solve this dense predictive task, you typically need a large architecture, data-hungry architecture. And so, by doing so, we generally make some assumptions that are often unfeasible in practice. So let's now try to review those main assumptions that deep learning generally does, and then we try to see how or which kind of frameworks can come into help and how can we employ them in semantic segmentation. So the first assumption is that generally we assume to have data available all at once in a central server, right? We collect all the data and then we train the model on a central server, and then we deploy this model to the clients or whatever we need, wherever we need. However, unfortunately, usually data is collected at distributed clients that then need to send this data to the central server in order to train the model. And of course, this raises some privacy issues, privacy constraints, right? The second main motivation is that domain distribution doesn't change at test time. So imagine we train our deep learning model on a high variety source domain, then we assume that in the test data and test domain, the data that we see, the domain distribution that we see is always the same. However, this is always not is often not the case, because you might train on, again, a bunch of source images, and then you go to test time, you never see those images, right? And finally, the third assumption is that label set is predefined and is not updated during training. So we decide that we want to train a classifier recognizing dogs and cats, but then at test time, and we do not update the model, then we see some new classes, some new samples, and of course we will have a wrong classification there, right? Instead, if we naively update it, then we will be able to recognize the new class, but we will forget the previous one, and this is called catastrophic forgetting. All right, so for each one of them, luckily there are frameworks now that allow us to tackle them and somehow mitigate the drawbacks. And those are namely federated learning, unsupervised domain adaptation, and continual learning. And we will try to briefly review each single one of them in this talk. So you might wonder why then is limited data? Is limited data in the sense that either data is not centralized, so it's distributed as clients, or maybe you don't have ground truth for the target data, or again, maybe you want to do continual learning, but in order to preserve previous knowledge, then you rely on some weakly supervised data that you crawl from the web, for instance. So this is more or less reflecting the outline of today's presentation. We will start with federated learning part that has been researched during my period in Samsung. And just to start from a very easy, I hope, introduction of what federated learning is. I think the easiest definition of that is a distributed machine learning framework that tries to learn a model on heterogeneous datasets. So again, in traditional centralized learning, we used to collect all the data from different clients, and then we train the model centralized, and then we send the model back to the distributed clients. In federated learning, this is completely the opposite, because data never leaves the device, and training is performed directly on the distributed clients. So you might argue, what's the difference then between distributed learning and federated learning? They're kind of similar, right? Well, I believe that both aim at training a model in a distributed fashion. However, the focuses are quite different. While in distributed learning, we try to parallelize the computing power as much as possible. In federated learning, we really don't care about that. We just care about training a model on heterogeneous datasets. All right, so we were saying in distributed learning, we typically take the whole data, the whole chunk of data, and then we distribute it to clients, and we roughly distribute the same amount of data to each single client, and we distribute the IID, so we simply sample in an IID fashion. In federated learning, instead, this is completely the opposite. Clients acquire the data, and those data are typically not the same size, because I might acquire a few samples, and other people may acquire more samples, right? And are typically non-IID. I might prefer cats, you might prefer dogs, and so on and so forth. And of course, clients are unreliable, because maybe I can disconnect my phone from the federated learning setup. So today's talk, we will focus in the classical centralized federated learning, where there is a central server that coordinates, orchestrates the federated learning setup. And so the server chooses the statistical model to be trained. It distributes the initial model parameters to the server, to the clients. The clients then train the model on the local data, and they send back either the results, either the updates or the model itself. And then we iterate these until convergence. So in principle, federated learning is as simple as this formula here on in the upper part. So the model parameters of the next step are simply a weighted average of the local model parameters of the current step, right? And I say weighted because there is an attention vector, the A there in blue, where it can take different formulations, right? So it can be in the original paper, in the federated averaging paper, they simply choose this attention vector as the number of proportional to the number of samples each client has. While there are some other works trying to model these as a function of change of the local weights versus the aggregate weights and so on. In the first work, we simply wanted to show the effect of data non-IIDness distributed across clients. So we simply decided to use a very simple function for the activation vector, which is 1 over the number of participating clients, basically. And what we notice is that, we took some federated learning data sets, we distribute data according to power law distribution and with variable degree of non-IIDness. And what you observed is that the distribution of this attention vector is actually pretty much different with respect to the federated averaging, right? So federated averaging here is in blue, and you can see that many clients really contribute little during the aggregation. They are between 0 and 0.1, while there are some clients, a few clients that tend to dominate the scene. So they have very high attention vectors. And this might be a big problem for convergence if you have data distributed in non-IID fashion, right? Because you will see always the same data and you will overweight the same models. So, okay, I realized that the line width here is not great, but what I wanted to show here is that even if in this simple aggregation procedure, if you distribute data high non-IID and in a power law fashion, then you can achieve higher results than the baseline federated averaging. And so we were thinking on how we could improve this federated learning aggregation by trying to model or to understand which kind of knowledge was learned by the distributed models, right? But which kind of knowledge was learned by the distributed models. And we noticed that all the standard approaches so far were employing only function of weights while aggregating those models. What we propose instead is to just bring prototypes awareness during the aggregation. So let me try to have a step back to define what is a prototype. So in deep learning in general, we are given a bunch of high resolution input images, and those are coming in a default representation. They don't have class information right at the beginning. Then we extract some kind of patterns, knowledge, features, let's say, and we build a representation which should be as close as possible to, or let's say as helpful as possible for the downstream task that we want to solve. So imagine it's a classification task, then we would like to separate the feature, to cluster the feature of the same objects quite, let's say, close one another. And so then the reconstruction task or the segmentation task or the classification task are easier, the decoding tasks. And if we do so, then we can simply take the centroid for each class that we have, and we build the prototypes, which is the star in this case. So yeah, coming back to federated learning part, we simply decided to change the attention vector to give this awareness of the prototypes as a function, is actually a composition of functions, one relying on the local displacement, which is computed between the local prototypes before and after the local training. So we kind of track the evolution of these prototypes during training on local data. And then we have an aggregate displacement, which instead tracks the change between before and after the federated learning, one federated learning round. Of course, there is a warning here because this requires prototypes to be sent over the cloud. So we need to send some kind of additional data to the cloud. But we argue that this brings only a minimal communication overhead, while typically prototypes are much smaller in size than model size. And privacy is still preserved since those prototypes are on average statistics and they can be easily encrypted. All right, so this is an eye view of the approach, and as a measure of distance, we use a margin of the class conditional features, and we will see that the centralized case maximizes the margin. So, just to have an intuition, if the margin is high, then the features are clustered well. Let's say the features of different classes are spaced apart between each other. While instead, if the margin is low, then we have a bit of confusion that we would like to avoid. So we started from some classification results, and we saw that our approach, called FedProto, was outperforming the other approaches. But what we were more interested in was to try to understand why was that the case. So first, we analyzed the margin of the feature learned by these federated optimizers, and we simply compute basically the margin of the final model of our approach, of the aggregate approach, of the aggregate final aggregate model. And so we see that the upper bound is given here by this gray dashed line, which is the centralized case, which is shown to maximize the margin separation between the classes. And we see that our approach in orange here was able to achieve some kind of maximization of the margin, given the properties that was prioritizing models having good properties, good margin separation properties. Then we went to analyze another metric of distance. In this case, okay, here we cheated a bit because we assumed to have a centralized training available. So we just measured the distance between the distribution of features computed by a federated learning approach and the distribution computed by a centralized approach instead. So imagine you have your centralized reference, which will produce some features like this. Then you have one federated learning model, for example, our approach, and then you have another model, for example, the baseline federated averaging. And we want to see the distance between those features. Oh, what happened? These features here and the feature of the centralized reference. Okay, so of course, it's a measure of distance. The lower in this case is the better, because we want to be as close as possible to the centralized reference. And we can observe here as well how our FedProto, our orange line here, achieves some minimization. So the features produced by our algorithm were closer to the features produced by the centralized train. Then we went to analyze some segmentation results, and we took the Pascal-VOC dataset. We distributed it according to different degrees of non-IIDness. And what we observed is that when data is particularly non-IID, our method was particularly successful with respect to federated averaging. And this was also visible in the auto-segmentation maps. Here we have FedProto on the right and Fed averaging on the left, a different level of non-IIDness. And again, our approach was better, especially when non-IIDness is in the data. We analyzed as well the confidence of the output softmax entropy. So basically, we computed the entropy of the final layer, and we see that the centralized case is always confident, so lower entropy, apart from the edge regions. And this is quite well mimicked by our approach rather than federated averaging, which especially when data is non-IID, we have really high confusion in this part here on the left. And finally, since we acted on the feature level, we also showed the entropy of the feature maps computed at the final layer of the encoder. And we saw that the features important or somehow, let's say, peaked in the centralized case were the same that we found in our approach, which were instead not properly recognized by federated averaging instead. All right, so I hope this was the first part. I hope I convinced you that data non-IIDness really makes a huge difference in federated learning. And I hope we observed a couple of quantitative metrics which could be of interest to analyze federated learning approaches. So either the margin between the prototypes or a distance between the feature of a federated learning approach and of the centralized training. And finally, some qualitative metrics based on entropy maps. That goes towards a direction of explainability. If we want to summarize this first part, we would say that a model is more than its set of weights. while previous approaches were only averaging according to the weights. In our case, we try to bring some awareness of what the model was learning, right? Or of how the model was learning. And so we believe the future federated learning approaches should also consider this while learning new, while aggregating new models. Then I'd like to move to the second part. As a disclaimer, this part was instead researched in a previous period in the uni. And I will not spend too much time because we have seen Gabriela's talk a few days ago. I will just briefly introduce what supervised domain adaptation is in our context. We assume to have some source data, for example, synthetic, large set with ground truth available, and with similar properties to the target data. And then we assume to have a target data set in which we don't have any label. And our aim is to train on source data set with labels and then try to find a way to achieve good accuracy on target data without any target label. So first of all, we analyzed where we could align those distributions or where we could adapt these models. And we defined 3 main levels, either at the input or the feature or the output. And then for each one of them, we proposed several approaches, which we will not cover here. I would like just to send some key messages, just to summarize our experience. And we believe that output level and input level approaches based on GANs are typically achieving good results because you can tweak the style of the images and so on and so forth. But they are hard to tune, unstable, and very computationally expensive. Now, however, some simpler methods based on Fourier transform or other style extracting techniques exist, so you might want to check them instead. Feature level adaptation, we found this to be very lightweight and more effective and could also be coupled with others. However, also in this case, we needed to carefully tune it. So this was also a main drawback. While let's say if you prompt me for a tip, I would say the data preprocessing augmentation really makes a huge difference in domain adaptation, but in general for all deep learning tasks. And so make sure you employ all the augmentation in order to have similar properties between source and target data first. And this is why this focus on data we see as a future evolution. And that's why we proposed a new dataset recently, which is a joint effort with another research group at my home university, where we produced this SELMA dataset based on the Carla simulator. In this dataset, we have more than 30,000 unique samples in 27 conditions. So in 3 times of day, noon, sunset, and night, and 9 weather conditions, as we can see here. It is multimodal in the sense we have 7 RGB cameras here in red and 3 LiDARs in green, and 7 depth cameras which are collocated with the RGB images. What can you use it for? I think you can use it for multiple tasks because you have semantic segmentation, object detection, depth estimation labels, and so on and so forth. So really, you can have multi-view predictions, weather level adaptation, time of the day adaptation, multitask learning, continual domain adaptation. You can really find your new next task. All right, so let me move on to the last part of the talk, which is about continual learning. Again, research during my previous period in the university. And again, let me start with a brief introduction and motivation. So in general, we train our networks and then we deploy them somewhere, but we would like them to keep learning, keep personalizing to the target user, right? And so in general, this property doesn't come for free in deep learning. And the key assumption is that you cannot always see previous samples to retain previous knowledge. So assume you have an initial task, which is fairly simple. You just want to space apart dogs from elephants, and you have a simple model with 2 parameters, then you will definitely find a solution because it's kind of a trivial task, right? But then you're given a new task, and this time you want to space apart other classes, and you use the same classifier, it will not work. You fine tune it, then you can make it work, right? And then you might deploy the final model in the real life, and you will see that it doesn't actually work on all the tasks, right? Because we just messed up while learning the new task. And so this is a silly example, I understand. In real world, we have much more complex architectures, and we want all the tasks to interact one another. So we want to solve all the tasks at once. And so this prompts us with a stability plasticity dilemma, where stability refers to remembering past concepts and plasticity to learning new concepts. So the key question here is, how can we find the trade-off? And I think we need to click again on the presentation, Raoul, if we can. Thank you.
Wait.
Yes.
There has been an internet problem.
Okay, sure. All right. And if we want to go back to the previous motivation, we saw that stability refers actually to not updating the model in this sense. So we are not able to learn new classes. And plasticity instead means, I mean, if we only achieve plasticity, then we only learn the new class while we forget the previous ones. And several ways to achieve this trade-off exist, and different methods have been proposed, either regularization or replay or so on and so forth. To go more in semantic segmentation instead, this is even more challenging because classes generally coexist and you have a dense prediction, right? So you might want to have some more complex architectures. And our contribution mainly relied on knowledge distillation or latent space regularization or replay-based approach. We will focus mainly on the last one. I think then later Fabio Cermelli will also give an overview of the first two. But basically what you can do to regularize training is to take knowledge distillation function and bring, let's say, bring some information from the previous model back to the new model somehow. So you can design some knowledge distillation functions. And if you do so, you can achieve fairly nice results, I would say, for such an easy method, where we have the baseline here, which is the fine tuning. So we simply fine tune on the new classes and join training where we have all the data distribution available from the start. And we see that it can achieve some good results. However, the main limitation we observed was that when you have visually similar classes, then this doesn't hold anymore. So imagine we trained our model, our network, with those three classes, cow, person, and bus. You see that we can achieve a fairly good semantic segmentation here. But then when you go to add new classes, which are visually related to previous classes, such as sheep and train, then you see that the segmentation really gets a bit messy. You are not able anymore to separate cows and sheep or to separate bus and trains. So we came up with the idea of maximizing the separation, again, of the latent representation, which is similar to the idea we saw before in federated learning. So if you leave the latent space unconstrained, then you might see that you learn these two classes, then you want to learn a new class, and you will see that maybe some features to learn the new class overlap with features learned previously to learn another class, for instance, right? Well, instead, if you constrain the latent space, then you can leave more space, more geometric space to accommodate new classes. Unfortunately, I cannot really go into the details of this, but yeah, this was the second part on latent space regularization. Finally, the last, let's say, bit of talk is focusing on replay-based approaches, where we acquire data every day. We might also tag it somehow, maybe an image level tag or multiple image level tag, and then we upload them to the web. So there is really a wide availability of those weakly labeled samples. But the key question is, can we make use of it somehow? And that's why we proposed this approach, which is named Recall. And the idea is as simple as this. So we take our current model and our current data, and we simply interleave those data with some replay samples. And of course, these replay samples, if we are training on the Pascal dataset, ideally would be from the Pascal distribution, right? But we assume not to have this distribution available. That's the key point. And we either recreate this through a GAN, a pre-trained GAN, or we download them from the web. However, of course, you cannot simply download images, even maybe pre-tagged image classification with an image classification label, and simply use them as they are, because they don't come with pixel level labels, right? So the first issue was that the labels for replay samples were missing. And so we had to generate some pseudo labels with some task-specific decoders. So basically, we took the decoders of the previous steps, and we saved them all. And when we come to a new incremental step, then we take those decoders and we produce the respective segmentation labels. And we analyzed that actually saving decoders really brings a minimal footprint to the average, to the total number of megabytes occupied by our approach. And the second problem was the background shift, which Fabio will explore later, but it's basically telling us that we are trying to learn a new class, which is maybe the person class. And we have already learned the bike class, motorbike class. And so we need to combine somehow this information, similar to knowledge distillation setup. And so we take the prediction of the previous step and the ground truth of the current step, and we try to merge them. So we merge only where the background is. That's why it's called background in painting. And this gives really an effect similar to knowledge distillation in this case. From the results, what we saw was that when you have maybe a few incremental steps, it doesn't really help too much. We were either on par or we were actually losing. But where we were gaining the most was where we had several steps, and we can see here the robustness, the high robustness of the approach over many incremental classes. Okay, some qualitative results finally shows us that even if we add similar classes, then we are able to actually recognize them, to space them apart. So for instance, sheep and cow, or bus and train. So if we want to have a takeaway on this last part on continual learning, we have seen how knowledge distillation really gives a great boost of accuracy, and it's a very simple way of bringing knowledge across two models. And we have briefly seen latent space regularization as an effective technique, and we didn't have time to cover them all. And finally, some replay-based approaches and background in painting in order to cope for the missing dense labels. And those are all approaches that are compatible one another, and they can be also applicable to other tasks. So that's the next challenge for you, how to extend some of those techniques to other tasks of your interest. So let's jump to the conclusion. We have seen how we could achieve transfer learning in semantic segmentation. So we trained our network, and then we want to deploy them in maybe a slightly different setup, or maybe we don't have data, and so on and so forth. And the next real challenge, I think, is how to combine them all. We have already started doing something like this. Also, other research groups are starting to explore this. For instance, we combined domain adaptation with continual learning, or domain adaptation with federated learning. And also, other next task is to really bring this, let's say, these models on device, or make them available to everyone. Then we should really try to compress them somehow to bring them on device, and finally fine-tune them for personalization for the specific user, for enhanced user experience. All right, this was actually the end of my talk. I'm not sure why what happened here, but yeah, if you have any questions, please.
Thank you very much, Umberto. If anyone has a question, please raise hand. Yep.
Yeah, there's one over there.
Okay, I thank you very much for the talk. So my question is, okay, is it a question? Maybe it's relating to the first part of federated learning.
Yes.
And yeah, so I think it's interesting to actually know that there is work going on in terms of evaluating the length representation on individual clients, right? And for instance, I was actually thinking about, because from the base understanding of federated learning that I know, it's like you have a central model that is sent to across multiple clients, right? And then the weights are being gathered. And now one of the things that I was thinking towards this aspect is, let's say, for instance, you train a large non-network model on a client, and then you send it out to different clients. And apparently one of the clients, the model is trained on a bad data, which means the representation, the weights comes back to the central model and probably like distorts the entire learning weights.
Yeah,
so
yeah, the convergence gets
so now one of my thoughts right now is now thinking towards, without waiting for the learned representation to come back, right? Is it possible for you to actually do that sort of filtering, if you can call it, at the client level? So what I'm thinking is this. I think I just considered some work that have been done in terms of, is it data brittleness, where you actually like kind of filter out bad data from massive data. And then I was thinking if that is possible in this case, where even before the models are updated on the clients, it kind of like data are separated so that we really do not need to now start looking at the learned representation back at the server model. I don't know what's your thought on that.
Yeah, no, that's definitely a good point. Thanks for raising this. So there are multiple ways, I think, to answer the question. It's not actually a question, it's more like a broad discussion, I think. For sure, there are two main levels where you can address this. It's either at the data level or at the model level, right? Because you're saying, what if you have bad data at a certain clients? Can you determine this? You can do it to some extent, but you should define a priori what does it mean to have bad data, because maybe for that client that data is meaningful somehow, right? Or maybe not. So if the data is only blurred images, then you might want to discard them, and I think you can do this a priori, but still raises some concerns because you're not taking into account that specific user, right? So it's not fair anymore, maybe for everyone. Yeah, I see you have another point.
Sorry, a follow up to that. So I just recollected now about there was a work somehow about like it's possible for you to actually do a modern analysis and then try to like, I don't know, let me ask, is it possible, like if you have a trained model, then you can figure out the data of which it was trained on?
All right, so
yeah, because I think I saw a paper that kind of like says something like that it's possible for you to actually, when you train your model, right, you can actually know which data this model was trained on, even without having access to the data.
Okay.
And so in case of federated learning, right, where the idea is privacy preserving, right? Now, if that's possible, then doesn't it render the entire federated learning approach somehow?
Well, yeah, you definitely can determine whether the data is good or bad before training the model, right? According to some prior knowledge that you have to insert, though, right? So you decide that maybe you don't want blurred images in your models because they mess up with the convergence of the federated learning approach. Instead, you can also do it a posteriori. So after you train the model, then you can try to either find if there are some out of distribution models. I try to understand why. Regarding instead your last question about can you determine which data was trained, which data were used to train a specific model, this is a bit more tricky, like how to extract. I mean, we don't really have so far a model, a way to understand which data was used to train a certain model, right? We can maybe try to guess some statistics of the data domain distribution that were used to train a certain model, but generating new sample, or let's say the same samples that were used to generate to train the model, then it's a bit more, it's a more complex task. There are some adversarial robustness approaches that try to do that, but still it's quite challenging. But yeah, definitely the point is interesting. I mean, if you have a bad model that is trained somehow or for certain reason, that can you spot it? Can you try to apply some out of distribution detector of those specific model across a suite of 10 models, let's say? But then you should understand why is that the case, and do you care about that or not, or you simply discard it? It's an open question. Yeah, but yeah, I think it's a very good point.
Any other last minute question? Yes.
Hello.
Hi.
Can you hear me?
Yes.
Okay, thank you so much. It was a wonderful presentation.
Thank you.
So my question is regarding the replay-based continual learning, right?
Let's see if we can get there.
For microphone, if you can remove the mask.
Oh,
the mask is not helping the mic.
Okay.
Yeah, you can start talking and it will take a while.
Okay, so for the replay-based continual learning, I see that there is a GAN there. So is it that you generate your images each time you want to combine the new images with the previous images? That's the first question. Do you generate your images? The second one is with regards memory. How do you manage memory? Is it that you have to like let's say, for example, you introduce your images in like 3 batches, right? Or the third tax. So by the third tax, you'd have 2 previous images. So is it that you have to generate each of these 2 previous images like by the third one? how do you manage memory, and how many classes are introduced per task or per batch?
All right. Yeah, that's actually another good point. So I think we can differentiate. I mean, when you go to actually deploy this in the real world, you can either choose to have like to store some generated images, so you might avoid to generate them in the future, or you have to generate them on the fly every time. And this is basically a trade-off, right? So how much memory are you willing to spend on this versus how much gain you want to, how much speed up you want to have in terms of computation? Because if you don't save any image, any generated image, then you have to either download them again or to generate them again. And this will take some time and bandwidth possibly, right? So yeah, this is definitely a good point. And according to the final application, then you might choose the balance on the trade-off. You might want to save a few images and then you can generate more if you need and so on. In this case, in this example, we actually generate them every time because it was just easier for us. But yeah, I mean, I think this is really up to the final application and the final constraints that you have. According the second question, the memory management part, we see here. So in this case, for instance, we add one class at every step. And we see that actually preserving the decoder doesn't really matter too much. So this is the line that tells us how much do you waste in saving the decoders. So it's not really much. Well, instead, if you would save all the images, of course, you would grow much more, right? And yeah, the difference between this and this is basically the web or GAN. So from in the GAN, you also need to store the model parameters of your generative adversarial network, right? So you have this gap here. While in the web crawled images, you simply download them from the web, so you don't need a GAN to generate them. All right, the last point was about
the number of classes.
Okay, yes.
Yes, number of classes per task.
Yeah, we evaluated actually on several tasks, and these were pretty much established in the literature at that time. And in this case, we have when we say 19.1, we are actually adding one single class. When we have 15.5, we are adding 5 classes all in one batch. Or when we have 15.1, then we have one class added at each incremental step. So we have 5 incremental steps and so on and so forth. So the most challenging one is the 10.1, where we train in the first step with 10 classes or 11. And then we add other one class at each incremental step. So we have 10 incremental steps. So yeah, in this case, in other works, for instance, in the previous work, we also evaluated on AD20K, where we have at most, I think, 5 incremental steps, each having 10 classes, if I remember well. So it depends also on which data you're interested in. AD20K has 20K samples, and it has like 200 classes. Or 150.
Okay. Sorry, as a follow-up question. So
very shortly, because we need to move to.
Yeah, we can also discuss offline. I'm happy. I mean, I'll be around today and tomorrow. So if it is a short one, we can go. Otherwise, we can discuss offline.
Okay, yeah, that's fine.
Okay, so don't hesitate to continue the discussion offline, sure. Of course, and I'm sure there will be other ones. Now we're going to move to the next speaker. So now for the next presentation, we are welcoming Sileye, that is a senior machine learning scientist at L'Oréal Research. He, by the way, was previously at INRIA for about 2 years, I think, or something like that.
Exactly.
Also the research institute where I work myself. But we have never met there. And Sileye has done his PhD from the famous EPFL in 2007. And notably for this audience, he has already given talk to Indaba, especially in the Indaba X event, right?
I used to participate to the Indaba X Senegal. So
okay, ex-Senegal.
I participated, I think, twice. So.
Okay, so he has done two talks already, but I think it's the first time in person that he's on site.
It's my first in-person Indaba, but I used to follow Indaba virtually. So I was very happy to be here. I'm very happy to be here.
Great, and he has a large line of work, among which many works on tracking for robotics, and more recently virtual try-on and some NLP as well, because I know that you're also working with some fellows here.
Exactly. So I'm doing.
So the floor is yours now.
Yeah, exactly. So thank you, Raoul, for this very nice introduction, and thank you everybody for attending to this talk. So my talk today will be about some work that I did with L'Oreal. So it's about real-time virtual try-on through deep inverse graphic and learn differentiable render. So virtual try-on is trying makeup virtually. So it can be makeup, but it could be clothes, but because we are at L'Oreal, what we are interested in is cosmetics. So this will be about cosmetics. So, and this work is a collaboration with some people at L'Oreal, so Robin Kipps and Mathieu Cord, and also it's a collaboration with Modiface. So Modiface is a startup that is in Toronto, but that belongs to L'Oreal. And also we have collaborator at Telecom Paris. So Telecom Paris is an engineering school that is in Paris. So it's one of the top engineering schools in France. So to give you some information about L'Oreal, because I think that this crowd is more toward tech giant like Google and Facebook. So L'Oreal is a beauty company. So it has 86 employees worldwide. So L'Oreal is owning 36 brands. So L'Oreal is let's say the mother company, and it has brands that belongs to it. So it has some billion revenue of 26 billion and some profit of 492 billion. So, and we are, as researchers, we are doing publication and patents. So in 2018, we have 505 patents. So, and here, if you don't know, you have all this, the L'Oreal family. So you might see products that you usually buy, and some of them you even know that they belong to L'Oreal. So you can buy them in supermarket, you can buy them in luxury in luxury shops, and you can buy them in professional product when you go to hair salons, for example. And you have also active cosmetics that are very close to medical. So L'Oreal can send product in any kind of channel. You can find them hair salon, you can find supermarkets, drugstores, travel retails, and you have all this product about hair care, hair color, skincare, and fragrance. So, and about the research, so L'Oreal has many sites. And for example, the main hub is in Paris. So you can see it's here. So the main hub is in Paris, but we have regional hubs, one is in the US or in New York, one in Brazil. So we have one in South Africa. So we have a site here in Kenya. So we have site in India. We have site here in Shanghai and in Japan. So L'Oreal is worldwide, and all these people are doing research, and research is about chemistry, biology, and people like me who are doing digital, so computer vision, machine learning. So today, just to talk about the real work that I want to present to you. So this is done in the context of digital makeup. So you can see this image. Here you have a woman that is trying digital makeups. So the makeups that you see are generated virtually. So it's not real makeup. It's a computer that is generating makeup around the eyes and around the mouth. So, and here we have this kind of products that help our customers to test our products. And in general, this is classically done using computer graphics. I don't know if you know the domains of, let's say, computer science, but you have computer vision, which is a big bulk. You have computer graphics, so you have machine learning. So in general, computer graphics is very related to, let's say, video gaming. So the process of generating images from 3D information. So in general, this type of task was solved using computer graphics. And the problem is that you have to be able using computer graphics to synthesize very complex material. And you have also it often needs manual parameterization. For example, if we want to build a system that generates this makeup, so there is a L'Oreal expert that will spend his time parametering the render so that for a given cosmetic, it will generate the right display. So it's very complicated to do manually. And this work is done in this context where we are developing machine learning to generate this type of visual directly from images, from examples. So classically, in fact, virtual try-on is done using, let's say, augmented reality. So augmented reality is something that you have like on Snapchat, where you can have glasses, you can add some let's say, some filters that they call in Snapchat. And for example, what you have here is you have an input frame. And so this person wants to try, let's say, a purple lipstick. So you have the big box here is the renderer. So, and its role is to generate like the image of the face with the correct lipstick, with the correct display of the lipstick. And so what you have here is that inside the renderer, you have a mesh estimator. So the mesh estimator will estimate the shape of your face. And you have also the illuminant estimator, and the illuminant estimator will estimate what is, let's say, the illuminant condition, like the environmental condition that are illuminating the face. And so we have the illuminant is extracted. So from the mesh of the face, we can extract the shape of the lips. And the renderer will blend, and in fact, using the illuminant and the lips, it will generate, in fact, the right color and the right display property on the lips. And this lips that was rendered with the right color will be blended back to the original face. So this is how we are doing classically augmented reality for virtual trial. Okay. So, and what you see here is that the lipstick parameters are, for example, the makeup opacity. So how opaque is the makeup that you are using? So what are the color of the makeup? So RGB. So for example, here is the typical color description. So what is the amount of gloss of the makeup? So how shiny it is. So how rough is the shininess, and how is the intensity of the reflection? So these are the parameters that parameterize the lipstick parameters. Okay. So, and this you can do the same thing for hair coloration also. So for hair coloration, you can have, let's say, this guy that want to try, let's say, black hair coloration to see if it suited him before he do it in reality. So we have the renderer here. It's another system that will take the face of the person, segment the hair, and it will like color a reference swatch hair with the color of the person. And we have a recoloring process that we color, in fact, the hair swatch to the targeted hair color. And this targeted hair swatch will be blended back using the renderer with the hair of the person. And this rendered, new rendered hair will be blended back to the original. So this person can test the black hair to see if it is good for him. And if it is good for him, he might buy the relevant product. So here you see a global pattern. The global pattern is that you have a face and you have lipstick parameters, and you have a rendering engine, which is done using computer graphics. And you can use the rendering engine to generate the virtual try-on. So the person with the tried lipstick. So you can do it for lipstick, you can do it for eyeshadow, and you can do it for hair coloration. So in the same principle. So, so here, in fact, what we propose us is, okay, we propose a self-supervised framework for learning an inverse graphic encoder that will predict the parameters of the lipstick so that the renderer can render directly, in fact, the lipstick without any manual parameterization. So we have a model that will predict what is all the parameters of the cosmetics, and that will be applied using the rendering engine. So, and so that we can have a system that can be running on real time, and that might work for all the type of application that we have. So here you have, for example, what we are targeting here is, for example, for lipstick, for hair makeup, for eye makeup, and also for hair makeup, for hair correlation. So now the method that we propose. So the method that we propose here is a diff inverse graphic encoder. So what is its principle? Its principle that is that, in fact, here we will do virtual try-on, but based on a reference image. For example, our customer will see an image with the lipstick that please her or please him, and our system will extract the parameters of the lipstick, and it will transmit it to the renderer, and the renderer can generate, in fact, using the picture of the person, the renderer can generate the person with the lipstick that is targeted. So here you can see the pipeline here. You have the reference image with the lipstick that is targeted, and you have an encoder. So here that will predict what are the parameters of the lipstick. So the parameter is the list that I gave you before. And so using these parameters that our renderer can understand, so the renderer can generate the image with the relevant lipstick. So it means that here there is no more manual parameterization. We don't need any more an expert that will spend, like, I don't know, 2 hours trying to fine tune the renderer to have the adequate appearance of the lipstick. So here, and the procedure is self-supervised. So here the procedure is self-supervised because, and in fact, what we can do is that we know what is the space of our cosmetic parameters, so we can generate randomly some parameters. So we can feed these parameters to the renderer given an input image, and the input image will generate the image of the person with the targeted lipstick, and then so our encoder can predict what are the parameters of this lipstick. And the parameters, we know it because it's the one that you have generated before, you have sampled before. So it means that when we are training, this system will train itself. So we will generate randomly these parameters. We feed it to the renderer with the correct parameters. The encoder will do its prediction, and our loss will be just the difference between the predicted parameters using the encoder minus the original lipstick parameters, the cosmetic parameters. So the loss is a kind of L2 loss between the target and the predicted parameters. Okay. So here the principle is simple, but you can see that there is a problem in this framework. The problem is in framework is that our renderer is a generic renderer that was built using classical computer graphic, and it's not differentiable. So because the renderer is not differentiable, it means that we cannot, when we are training, we cannot differentiate through the renderer. So in fact, what this loss is doesn't see what's happening in the image space because there is no differential with respect to the original input. So to solve this problem, so what we did is we added an imitator, and the imitator is a kind of network, and it's a GAN, it's a generator that is able to generate an image the same way that the renderer is doing. So you can see that the imitator is an approximation of the renderer. It is doing exactly the same thing, but the imitator is a network, so it is differentiable. So it means that when we want to differentiate, and so that our encoder can see what's happening in the image, so we can here in this pipeline we can differentiate through the imitator, so that we can affect the renderer, we can affect the encoder based on the difference between this image and this one. Okay. So that, in fact, this is why we need the imitator. The imitator is let's say it's a network. So our original renderer is a black box. So we get it from legacy. Some people have developed it like years ago. So we are using it. So we approximate like the renderer by an imitator. So, and in this way, we can train the imitator similarly with the graphical loss that I showed you in the previous slide. And also we can use also here an imitator loss that makes the difference between what the imitator is doing and what the renderer is doing. Okay. So here we have an additional loss, and the loss here is done in, it's what we call a perceptual loss. So if you look at the bibliography, so the perceptual loss is that you don't compare directly the pixel, but you compare the internal layer of, let's say, pre-trained model like VGG. So in this type of model are more robust than the pixel-wise loss. So because you can deal with images that are not aligned, but the content are similar. Okay. So here, and and to better train our imitator, so what we add is what we call a sensitivity loss for the imitator. And the sensitivity loss is where we want our imitator to behave the same things than the renderer. So in fact, the imitator, we have first given an image, we have a parameter, and we will generate, given an image, like an image generated by the renderer, an image generated by the imitator. And then we will do some perturbation to some component of the parameters, and we will generate an image with the renderer and with the imitator. And then the difference between the image generated by the imitator, renderer, and its perturbation should be similar to the difference generated by the imitator and it's the perturbated version. So we want that every perturbation that you have in the parameters, so the imitator will behave the same than the renderer. But because the original renderer is not differentiable, so this is the way that it's a kind of finite difference. So we are doing some finite difference in the parameter space so that we can make the original renderer vary, and the imitator will have some variations that are similar. Okay. Okay. So, and just to give you a summary of the system here, I put all the losses that are used in the system. So to the left, you have the loss of the imitator, and to the right, you have the loss of the encoder. Okay. So, and the basic loss is the perceptual loss. And as I have said you, in fact, the perceptual loss is, okay, the features extracted using a VGG model minus between the target and the prediction. Okay. And then you have the perceptual loss between the imitator and the renderer, so that the imitator is doing the same than the renderer. So you have the sensitivity loss that is granting the variation between the on the parameters will have the same impact on the imitator on the renderer. And you have also a GAN loss, so that I didn't present, but it's here, it's anecdotal, but the GAN loss is just here to make sure that our imitator is generating images that are realistic. So that cannot be recognized, so that we cannot recognize the true image and the one that are generated by the one that are generated by the imitator. Okay. So these three losses are combined to give the loss that we are using to train the imitator. And here you have the loss that we are using to train the encoder. And so you have the graphic loss that is comparing the parameters, input parameters, and the parameters predicted by the encoder. And also you have a difference between the render image and the parameters that are generated by the imitator when you feed the parameters. So here you can see that, okay, here we can differentiate to the loss so that we can affect, in fact, the encoder using the imitator. Okay. And so if you think about it, principally, in fact, the imitator is here for us to train a loss that help us to build a loss that help us to train our models. So in fact, in reality, we're in our production system, we are not going to use the imitator, we just use the encoder, but the imitator is just a loss. So in fact, introducing the imitator is a kind of training a distance that allows the encoder to see what's happening in the image space. Otherwise, it won't be able to do it. Okay. Okay, now to show you the results that we obtained. So here you have our complete pipeline. And so for the lipstick, we have a reference image. So we have a source image, and we have the lipstick that is transferred from this reference image to this customer that is testing. So it means that here our encoder, and the principle is that our encoder will extract the parameters of the lipstick from this image, and it will give it to the renderer, and the renderer will just take this image and generate this image. So there is no more manual intervention by any expert. So we can do the same thing for eye makeup. So we have the eyes, we extract using an encoder the parameters of the makeup, and we can transfer it to this person. We do the same thing also for hair coloration. So here you have the reference hair color. We extract it using the encoder, and we apply it to this person using the encoder, using the renderer. Okay. And we can do the same thing also for very complex hair patterns. So you have here various results for different person and different lipstick. Okay, so I'll go faster. So different person and different lipstick, and you can see that, okay, for very different person and very different lipstick, from pink to dark red to purple, okay, you can transfer it very smoothly. Okay, so we did also some, let's say, some ablation study which are classical. So to see what are the impact of the different loss, because here we are training with 5 loss, and we have to check that these 5 are really effective. They are doing something, otherwise they are useless. So, and in the first row you have the source image. In the second row you have the result when we have trained our system without the sensitivity loss. And in the third row, you have our imitator with the sensitivity loss. You see that the sensitivity loss is really good at making our encoder able to predict, like let's say, the glossiness. So the color is good if you don't have the sensitivity loss, but you don't have the glossiness. So if you look at the lips here, you are missing some glossiness. So, and we did also some more ablation studies to see what are the effects of the different losses. And let's say the take-home message is that the complete model is performing better because it's at the same time it allows us to clearly model the color and the specularity, so the glossiness. So here you have a video, and for the video, what we do is that we extract the lipstick parameters on this one, the first on this one, and we just apply it to the video frame by frame. So here is how we do when we apply the model on your cell phone. Okay, and you can see that like for different person we have the lipstick, so that is well transferred. So this one purple lipstick transferred to this person, and sometimes like here you have like skin, like nude lipstick that also can be well transferred with the glossiness. Okay, to go a little bit faster on, so we do the same thing also for hair coloration. And so we transfer here this dark hair, this person, and so her hair are darker. But okay, sometimes we see that some drawback because in fact the hair in the previous are darker than in the original are darker than in the target one. Okay. Okay, so in fact, this paper is a paper that was published at Eurographics 2022. So if you want the detail, you can have a look at the paper or send me an email. But what we can see is that we compare our method with state of the art. So state of the art, so we have GAN-based method and other method. And so on our data set, we see that our method is performing better. So with respect to classical metric, because these metrics are supposed to be correlated with visual perception. So this method are favored by the community because if you are better, it means that a human being will prefer the best one. So also we compare qualitatively to see, okay, what are the different between the different method, and you see that also our method is performing very well with respect to state of the art. Instead, the only place where we are not performing with respect to state of the art is for the hair coloration. Here, the state of the art Michigan is working better because it's capturing better the hair glossiness that we are not capturing that one. So also our system can run on real time. We did some benchmarking, and so we did on Safari on iPhone 8, and you can see that our method can run on real time. So just to conclude my talk, so in fact here I presented you a deep learning based method for virtual try-on that is coupling an encoder and an imitator. And so this system is working well. We have it in production, but we are not really satisfied. We have some work to do because in fact, this system is not using any 3D information. And we know that the information that we are trying to address is 3D because when you talk about reflection, all this, you have to go into the 3D space. So for us, the next step is to study this problem into 3D. And also they have some strong problems that are related to the ambiguities that are due to the interaction between the appearance and of the person, of the environment, and of the illuminant. Okay. So, so this concludes my talk. So if you have questions, I will be happy to take them.
Thank you very much, Sileye. To switch it on. For your presentation. We have time for one question. I'm sorry, we're being a bit pushed towards the coffee break. Anyone has a question?
Thank you. Yeah, thank you. This is a very fascinating work because one question I just really wanted to highlight while you're discussing was how this compares to using these style GANs or is a BOT GAN or something. And I think I saw the result, but my concern now would not be in terms of computational efficiency, like how, because since you're using 3D, you're estimating the parameters in 3D, and in comparison to other GAN model, do you sort of compare the performance?
In fact, the way that we are doing is very efficient. Because in general, classical renderers are faster than neural networks. So classical renderer is the one that you use to generate video games. For example, if you are doing video games on your computer, it's not a GAN that are generating the image. It's a classical render that generates the image, and those are faster. So it means that our classical renderer that we use here is faster. So that's why we are not replacing the renderer by the imitator because it's slower. And the encoder is just, it could be a CNN, but we are using here an efficient net. So it is supposed to be a network that are very efficient. And you can see here that it's very fast. In 57 milliseconds, the image is processed. Okay. So it's really fast. It run on real time on your cell phone. Yeah. And the GAN-based method are less efficient because GANs are big. So you have to use UNet-like method, and they are really big, and they are more like computation. Okay, so a follow-up to that would now be okay, maybe I will see you later. Sorry? Okay, no problem. We can talk during the coffee break.
Okay, let's give a hand again to Sileye.
Thank you.
So the next speaker is Gabriela Csurka, and you probably have already seen her if you've been a full week attendee, because she has been giving a plenary talk on Tuesday, right? And really happy to have Gabriela here presenting again a different presentation just for her to have more work. And a brief introduction, because she was already introduced, but she's principal scientist at Naval Labs Europe. She's also an author, the author of several books, including the last one that I can only recommend, the one on visual domain adaptation in the deep learning era. You notice it's the same title as the keynote. So, same content, I guess, I hope with more text. Sure. And she has, of course, worked a lot on domain adaptation, but also other topics like localization, and also anything related to image understanding, general image understanding. And another important part of her work is that she's the main inventor of the bag of words. That is something that has been reused by the community for long and still being used and readapted to deep learning strategy as well. And last, maybe anecdote that I actually learned recently. She's one of those that never stopped coding. That's an important thing, because there are not many people that continue coding through the years. So thank you, Gabriela, for being here. And now the floor is yours.
Thank you for invitation, and thank you for being here still so late. And thank you for the introduction and the invitation. I'm happy to present you now. It's a bit not necessarily my work, because as I said, I work on many things, and I try to find at the lab works which were more related to the workshop. So you will see that I try to present some of the works of my colleagues, and not too much from myself. And also some of the recent current work I cannot present in our cases. So let's see about what we are doing in the lab. Some of the works, I mean, this is just a few works I selected from our lab, which I found they are the most relevant for this workshop. And we have seen today and yesterday, I mean, previously also, that deep learning was one of the main ingredients to success for many tasks. That one includes also the semantic understanding. And of course, what is the important with this, that there is a large image collection on which we train the data. We have deeper and deeper models, and we have seen Mathieu talking about transformers, and they require a lot of power. But one of the key element in these models, at least the first models, was what we call the annotation hell, meaning that these models often require a lot of label. And I would just repeat what others said, that annotation, especially pixel level annotation, is extremely costly, and in some cases even hard to obtain, like in medical field. And what are the solutions to overcome such limitations? So there are many technologies we try to use the data, unlabeled data, weakly labeled data, and so on. So this is just a list of different techniques which can be applied. I mean, you have seen the domain adaptation, that bigger one is the transfer learning and semi-supervised learning and weakly supervising. Some of them you have seen incremental learning. So I try to fit also these works in these settings, and I start with some of the work in self-supervised learning. And self-supervised learning is a sort of, we have on one side a fully supervised methods which require fine-grained annotation, sometimes expert knowledge. And on the other hand, we have a big data set, but where we don't have annotation, and we try still to get some knowledge out of the model, out of the data in a self-supervised manner. So just to situate the self-supervised learning between the supervised learning, which takes these high-quality manual annotations and try to learn a model on that, and an unsupervised learning, which actually try to work only with the distribution, with no training, for example, learn some clustering, some representation. The self-supervised learning is still a supervised, that's why it's self-supervised learning process. But actually what's happening that the model, the method itself, it generates itself the labels from which it learns. So self-supervised learning, I mean, it's already was previously some works, but some of the early works were in denoising decoders type of methods, which sort of perturb the image and then try to reconstruct, or doing some simple randomization or colorization of the model, and then try to learn some generative model. And then there was also works in mask modeling, which was more around the language. And more recently in images, the masked autoencoder combining these two ideas. And in parallel, there was also the semi-supervised, the self-supervised, discriminative self-supervised learning, which used some pretext task to learn. And this was, for example, the early work of jigsaw puzzle, cutting the image in different parts and try to reconstruct, or image rotations and try to predict. And also some sort of joint embedding model based mainly on contrastive learning. And if you are more interested in this self-supervised learning, this is this is a quite nice survey on arXiv, very recent one, where you can get a lot of detail about all those methods. And here what I want to show, it's the work, the Moshi, which is a work of some of my colleagues, Yanis, Bülent, Noé, Philippe, and Diane, presented at NeurIPS 2020. And actually, just to get to this contrastive learning, the self-supervised learning based on contrastive learning, the main ingredient here is that the proxy task is instance discrimination. So the main idea that if I have a query, I can generate some version of this query by doing some augmentation, and then this image the representation of this image should be closer to this image than to any negative images, for example, dogs, but also other cats and so on. And this was shown in Moko, that this already allows the model to learn quite a nice presentation, which generalizes better than even many supervised representation learning. And then some people said, well, what about how to make it the model performs even better? And for example, by creating better positives, this was for example, this handcrafted data augmentation in SimCLR. And my colleague says that, okay, and what about if we create better negative pairs? So the idea of a mixing of Moshi, mixing of contrastive hard negatives is very simple, that we take now the hard negative mining, and we get this mining which we keep, and then use these ones to generate more hard negatives. And this is simply either by mixing two hard negatives together or by mixing the hard negative with the query. And this they show that allow to improve, for example, MoCo, not only improve the generalization performance, but also to train quicker. We are also working, one of the current work, we are also working on self-supervised learning, but the aim is here is to try to address 3D tasks, and this is a bit more in the mask autoencoder side, but as I said, I cannot tell too much about, but the idea of mask autoencoder, instead I will show what's about the mask autoencoder, and this is a transformer network also, but actually when we can cut the images in several parts, and then the main idea is that if we try to mask out many of these patches, and we give the encoder only the visible patches, and then we get these tokens, and these tokens then are put back in a bigger representation, and the masked one is they are just replaced by a so-called masked token representation and try to decode the images. And they have shown that with this method, we can here we can see that when the image learned well the context and the semantics of the images, it is able to surprisingly well decode the images, even with the very much masked images. But we see that, for example, here when we don't have nothing about the cucumber, then it begins to predict tomatoes, but it's sufficient to have a few patches, and then the model is able to predict well, to reconstruct well the images. And this pretext task helps quite nicely to learn a very good representation, and then we can see that it can perform better than even this contrastive loss, especially in a large representation space, for example, here on semantic segmentation. So what we think is to try to go further in this direction, and actually learning from 3D scenes, our aim is to learn a representation which is not only works well on the semantic task, like segmentation classification, but the aim is to learn some more geometric related downstream tabs like depth estimation, key point detection, camera pose estimation, and so on. Then we already see that text and images can be also combined. So another way of weakly supervise the model is language-based supervision. So we already seen this this morning, and this can be situated a bit in between, where we have the images, but not only the images, but some text which is aligned with these images. And this is a very rich information. It does not require manual annotations because we can acquire this kind of data with parallel text. And then we can use these weak annotations to learn representation. And this is another work by Diane and Bulent and here Julien. And they have shown that they were also amongst the first in 2020, they already exploited the transformers in this cross image representation learning. And they proposed the image condition mask language modeling, where actually the idea is that we take the text and we take a BERT model, which was very successful in text, and then on the other hand we take the visual representation and we try to learn a auxiliary multimodal network in order to learn what it is to learn a better representation. And here actually is that we try to take this model to predict the mask token, not only by the text where the text representation is frozen, but also using the image. And their model is, it seems a bit complex, but actually they have this language model, the BERT one, and from the image they have a simple CNN where you have the text feature, and then they compare with the tag prediction directly from the, if they learn to tag prediction directly from the visual representation, or they propose two different models, one where they take just a transformer, a cross transformer or cross attention model between the image and the text to predict the missing token, the label of the token, or they also use a sort of pairwise attention model and a fully convolutional layer. And they have shown that actually with this language-based self-supervised learning, they can perform quite well on different downstream tasks. Of course, on ImageNet, because the supervised model was built with the ImageNet model. The best model is, so this is not a transfer learning task, but for the other ones, they can have and also VOC, which has very similar labels than the ImageNet. They do not perform as well as the full ImageNet when it is used the full label data set. But if we reduce the ImageNet and we take less images to train, then which is more comparable about the images they used for their training and for example COCO, then they outperform those methods in these downstream tasks. And also furthermore, they have shown that the model learned also to sort of localize. So when if they mask a word, then the model is able to show on what it relied and where it looked to in order to get the predicted labels. And of course, it predicts several labels, but in general, it also able to predict the stripe. But this was on the training, but they also, in the other case, when they use this transfer, then of course this is a representation learning, and then the model is fine-tuned on the target task. But this was quite early in the time when all these papers come out almost in parallel, combining BERT with visual representation. But since we have seen this in the first clip, for example, which was also successful, and DALI and Align. So these models which are try to combine in the transformers visual and textual representation. And for example, here there is a few models, and again, there is a survey on Archive, which is quite on transformers in vision, and they show that, yeah, in many cases you can take the visual and textual representation and do these cross-attentional models, but also you can first encode the language and the visual representation, and then do this also with transformers, and then use a cross modality transformers. And it's not limited only to text to image. We have videos, we have audio, and so on. So I really advise you to look into if you are interested in transformers in vision. So this was the first part, which was the self-supervised learning. And then another line of work is more on lifelong continual learning, because this is also very interesting. And we have seen already the continual learning in the previous talks, that the aim is here that humans and childs are learning continually, relying on previously learned tasks and improving their self. And the question is, can we do the same in machine learning? And here I'm mainly focusing on continual domain adaptation. So Tuesday I talked about more the classical domain adaptation, when we have a source and a target and a labeled source and an unlabeled target, and then we are passing from one to other data. And here I'm talking about, I mentioned these, but here I will show two works. One is in the incremental domain adaptation, and the other one is the online domain adaptation. And the first one is, the idea is that we have a source domain, which we learn with the labels, we learn this domain, and then it's a new domain which is coming, and then we try to adapt for this new domain. And then it's another one and another one. And the aim is indeed, we already heard mentioning the catastrophic forgetting. We want to do all this, but without forgetting the previous task. And on the other hand, the online adaptation is a sort of test time adaptation where we don't have these distinct domains, but we have a sort of target domain which is not necessarily known, which is continually changing. And actually we want to adapt the model one element per element, or maybe a few, but this is about online. So the first work is by Ricardo, Diane, and Gregory, and they have shown that to do this continual or incremental domain adaptation, actually they can combine randomization and meta-learning. But so what is the task here? I already mentioned a bit that, yeah, well, for example, in autonomous driving, the car starts with a model, with a sort of pre-trained model on some images, but then it meets other conditions, and then other conditions, and it wants to be able to perform well on all these conditions. And actually, one way, another solution is that to keep all this data, or at least partially, and then use all the time recompute the model. But of course, this is time consuming, this is computationally consuming, might have some privacy issues. So maybe it's not the best way of doing, but anyway, they propose here an alternative solution where they don't need to save, to keep these samples. Instead, what they are doing, that considering a current domain, they say, okay, the distribution is rather small and it will generalize not very well. So what about if we try to extend this domain with the domain randomization? And Ricardo, who is expert in domain generalization, domain randomization, so he said, okay, let's apply this. And even just applying the domain randomization, we see that we already get quite a powerful and much better than the baseline in these settings. But another idea was to combine it with meta learning, and more concretely, they use the MAML in this sense. And so what the idea was that they try to learn for the current domain, and then the training, they try to adapt fast on these domains, but also propose a loss which performs, which allows them to, in the backward transfer, to mitigate the forgetting. So if you are interested in the paper, you can go in and see more details. I won't enter too much in the details, but the idea is that they start with a domain, then they propose these auxiliary meta domains to increase and to train the model, and then they go to the second and so on, and they show that these 3 steps allows them to get a much lower forgetting. Still there is forgetting, for example, in these semantic segmentation experiments, when they try with a clean model and then a foggy and a cloudy, then there is some decrease of the performance in time. I mean, still when they are on the clean is great, but then when they train the model on the second domain or the third domain, this is on the clean data, so tested on the clean data, they have a drop. And similarly, we can see that when they train on the right one, it's higher, but for the other ones. And here the blue is the one which is just the domain randomization, and we can see that just using the domain randomization also works quite well, but with the meta learning, this is improved. And to finish, I will just mention a work where I'm co-author also. And so here, what we proposed in this CVPR this year is OASIS, on the road online adaptation for semantic segmentation. Actually, it was more to propose a benchmark for online adaptation of semantic segmentation. And as I mentioned here, the images come one by one sequentially, and the environment continually changes. And we have a sort of starting model, and then we want to adapt by frame using for the current frame, and keep going. Actually, this online adaptation of semantic image segmentation is an intersection of many fields. Actually, this is because we are also starting with domain generalization and adaptation. Then it's also about continual learning and image segmentation and online data. So we have shown that this is really a sort of intersection of many domains. And also, on the other hand, we have seen that the existing benchmarks SDR are not suitable to evaluate such model, because generally in a domain adaptation, you have to think about that especially in this case, if we have labels for the target data, then why not using? So we cannot use even the any target data to select our models, to select which is the best model, how to handle. So instead, in domain adaptation in general, but for example, here also, the best way of doing is to have a training set on which we train the model, and then to have a validation set on which we validate our model, and then a deployment set on which we test our model. And this is not only proper to OASIS benchmark, but it's more for domain adaptation, it's the best way of doing, because even if it's not always done, it's a better way of evaluating, because if we use the target data, even if it's in inductive or transductive settings, still we used the target data to validate. So if we had those labels, why not using? But this is just in parentheses. So here we really try to make a benchmark which is really properly set up, and we also took existing data set, but we built in a way that let's train the model on GTA, and then consider another data set for a validation set. And here we choose Cynthia, but I think Clara could be also very nice validation set in this setting, because it's exactly if they have these sequences and if have this variation of domains, that's perfect. And then in the deployment set, we don't test many models, or many parameters, but really use the best parameters obtained on the validation set, and we test directly on the test set. For example, here are ACDC settings. And of course, here we wanted to test several methods, how to cope with catastrophic forgetting. So we also considered, as I said, domain randomization was more to, and we have shown that domain randomization is very good to be performed on the source data to make, as previously also I have shown, helps the generalization performance. So this allows to get a better initialization. And then we tested several methods as a test time adaptation. There was some batch normalization based or self-training based, and kind of test time adaptation methods, and we compared several ones. And then in order to avoid catastrophic forgetting, of course, we had the naive model where each frame will adapt from the original model, and forget, in that case, it does not forget the source, but the question is that performs better than the others. We used also we normalization, or also sort of memory replay kind of a method also. And finally, we proposed also we tested some research strategies, meaning that we try to measure if the model starts to forgetting, and then we only, in that case, we reset to the original model. And here is just, I mean, the code is available at this place and you can play with. And here we can see that, first of all, one observation was that when we compare all these methods between the validation and the test set, we were happy to see that there was a sort of a coherence, meaning that improvements we get on the validation have shown up also in most cases on the test set. And actually as test set, we use the ACDC, the cityscape original, and the cityscape where artificially there was fog and other enhancement and their modifications in the sequence. And then of course we compare these naive adaptation methods and continuous learning, and we can definitely see that the continuous learning, if we just apply as it is, it drops drastically, and really we need to improve over that with some of these techniques, like, as I said, source regularization or reset strategies. And actually the tent with this reset strategy performed very well, but also the pseudo learning. So this reset strategy worked quite well. And the Oracle reset strategy is just that we test, in this case, we use the some measure on the, here we measured, for example, the number of classes if it started to drop or this. And in the Oracle, the only things which is different is that we knew that if on this new image is this original one better than the new model, and then we replaced and we did this reset strategy. So this was just a sort of experimental comparison, and if you are interested, you can see in the paper. And also we wanted to propose this benchmark for further work in this continual learning. So here is just an example that how the model is do this very big drop in that case, and in some cases we can get better with this pseudo labeling and reset strategy than with the others. But this is just an example, and we have also stream code to make some visualization in the GitHub. And so to conclude, yeah, we wanted to make a benchmark which tries to imitate the real world, how it is faces with this continuous distribution shift. And that's why we proposed this OASIS benchmark. And some of the findings was that domain randomization builds a much stronger much stronger initialization, and this is very important. So if we can already improve over the initial model, that's very helpful. But then naive adaptation, if we just do naive adaptation, we really see this catastrophic forgetting, and then we have different ways of avoiding this. Oh, that's all. So thanks for your attention. I want to make a special thank to Diane, who provided me with some of these slides, even if I redraw a bit, and I'm happy to answer questions.
Thank you, Gabriela, for your presentation really well. So if there is any question, don't hesitate to raise hand.
Thank you, Gabriela, for your very nice presentation. So I have a question about catastrophic forgetting. So is catastrophic forgetting a phenomena that is well understood, and are the solution like a real solution, or are solutions that we hack that we put so that we try to avoid it?
I mean, catastrophic forgetting, we have seen also in other talks that, yeah, it exists indeed. And of course, because you are training on a data or on one task and then, or one domain, and then you are completely on the new domain. So when you fine tune, even if it's supervised or you try to adapt, it happens that the model will start to focus on this new domain, on this new task, and it forgets if we don't do anything. Then there is many things to be done with this replay one, for example. So often people try to keep, but that's the inconvenient, is that the memory issues and regularization can help a lot. And what we proposed here is that this reset strategy, but this is one of them, saying that, okay, we put all our effort to have a good starting source model. So if we begin to feel that our model, and here is the question is how to measure that my model, it begins to be uncertain, it begins to lose. If you see here, for example, also in this image, I not entered, but here, for example, this is a continuous learning. You see all these some of the classes completely disappeared, and there are other. So the model simply do not see for a while persons on the road. It might be that then it completely forgets the person class, and this can be very fatal in autonomous driving. So that's the main problem here. And then this reset strategy is just one possibility, is that, yeah, my model I trust, and it was sort of quite good, then why not resetting it? But the question is how best take the two out of order. Here we tried a few strategies, we compared a few of them, and actually what we wanted is more open the field than giving a solution to solve this.
Okay. So sometimes probably you want to forget because your data is drifting and the old model is not valid anymore.
Yeah, that's another thing when you want to forget, but then you encode it in this way. Of course, this is another, but here in autonomous driving semantics, generally, I mean, you want to be able to handle. Yeah, of course, if you get a very out of domain distribution class, that's another point. Should I integrate? Should I use as just an out of distribution? That's another line of work.
Okay. So can we use all these techniques that are used for GANs, so that when you are training GANs, you have this problem of mode collapse because they are disappearing during training? Is it related or not?
I think these ideas are completely unrelated for the model. So I think it's here. It's this continual learning can work for anything. I mean, the autonomous driving semantic understanding is a very real problem, and easy to see how it is, but it's not limited. So these ideas, the test time adaptation, it was proposed for many things, and the classification, segmentation. So it's not about that. Here also, and the first point, wanted to point out also the importance that in a real situation, we cannot say that we tune the model on the target set, because the target set, if I have labels to tune, then a better strategy is use those labels to train. So that's why also these three steps, which is important in the adaptation.
Thank you. I said, please, if you don't mind, could I quickly share something as well, like in addition to what you said?
Yeah, please. Yes, of course. We are here to discuss. Go ahead.
Okay, thank you. So please, I want you to picture this. See this? Okay, yeah. So please, I want you to picture this for catastrophic forgetting. Imagine you walked into a room, you as well as my fellow volunteer here, Daniel. If you walked into a room and someone sees you, their memory is fresh of you, or both of you. Or if two new people walk into that door, right, their focus might be more on the two new people. So the way catastrophic forgetting or catastrophic inference works is such that when a new data is introduced to a model and your model is trained with that data, so the model is able to learn on that data. But by the time you introduce like a new set of data, right? So the weight of your model would be updated based on the new set of data. So it's that there's this thing called a weight drift. So there could be a weight drift or a weight change. So what will happen is that your model might most likely be predicting more on the target of the new data rather than the previous data. So that's how catastrophic forgetting or inference works. So thank you.
Any other questions? Otherwise,
okay. Thank you very much for the great talk, first of all. You told us about continual learning from the sense of domain continual learning, right? So you started in this example, your rain, night, snow, fog domain, but maybe the underlying image is coming from the same city or even the same kind of region, let's say. Well, okay. So there are a few questions that I have, and I don't know if you have ever explored. Like sometimes you might have different semantic concepts as well in different either regions or in different, let's say, time of day. For instance, you might have semantic concepts that only happen at night or only happen when there is snow, such as, I don't know, the snow removal track, for instance, you just see it in a specific context, right? Or something like that. Or even if you think about instead of rain, night, snow, we think about different geographical regions, then we might have tracks or we might have specific cars just for their regions. And so we have also semantic shift in addition to appearance shift, as in this case, time of day, or let's say weather shift, weather level shift. I don't know if you've ever explored this also from the perspective of
we a little bit explored
semantics.
in this data set, but it's slightly when we try to take in the cityscape, we build sequences where we take image sequences from different cities and different conditions, and in the paper you have some of them. Of course, it's very artificial and for this data set, but this is a very good point, and we also thought about, but this is the next steps to how to add also task shift. For example, you might have in some for example, the IDD data set, you have I don't know, the tuk-tuk or how you say in English, and this is not inside, but these are next steps. So that's why I said that this is an opening of the field. Of course, then you have to handle domain shift plus task shift. Definitely, and very interesting and very relevant question. I completely agree with you. And this is the future, I think, in this field. And then we have also...
Thank you very much. Maybe just a last yes/no question. Why using Cynthia? Because it has discrete weather. Would that help to go towards stuff like shift or?
It has discrete weather and sequences. And we wanted to simulate a sort of, we could sort of generate some sort of multi sequences where you have a motion, and then you have a sort of sequences, and when you have parallel sequences with the same. So I don't know, Clara, how it is and how it could be used, but yeah, probably could be also interesting, but that was our aim, that using the Cynthia as a sequence, but other data sets coming, so I think it's interesting to get maybe also as a validation set, real one.
Thank you. Let's give a round of applause again. So as next speaker, we're welcoming Fabio Cermelli, that is here. He's currently a PhD student in Italy. He's last year actually PhD student from the Politecnico di Torino. I don't know if the pronunciation is fine. He also did some visiting research during, I guess, your PhD in Trento University, and he's working on incremental learning, few shots, federated learning, and mostly with application to something related, since robotics and autonomous driving. So the floor is yours. Give me 10 seconds to start your presentation.
So hello, everyone. Today, I will speak about weakly and partial annotation, especially for semantic segmentation. So I started with an introduction about myself, which has been already made, but few words can help. So I'm Fabio Cermelli, and I'm last year PhD student at Politecnico Torino. My main works are about weakly supervised learning, semantic segmentation, and incremental or continual learning, whatever is preferred. And yeah, in my time, I love football, reading, and fighting against neural network, and most of the time they win against me. Okay, so you probably know what's semantic segmentation right now. Just a brief introduction. So in the semantic segmentation task, you want to have every label, every pixel of the image label with a semantic category. So for example, in this image, you can have a lot of classes like road, car, person, and you want that every pixel is labeled with something, and you want a model to make it by itself. So what's the point of, how can we train such a model? So first of all, of course, we need to collect a data set. And the data set needs to contain thousands of examples and needs to have per pixel annotation. So every pixel of the image in the data set should be annotated with a label. And then we need to train a model for a few times, maybe hours, maybe days. And then we need to deploy the model in the real world. So there are a lot of issues in this kind of pipeline. You can have issues in deployment, you can have issues during the training, but today I will focus especially on the first problem, which is that the data set is super expensive to annotate. So before someone spoiled that annotating the semantic segmentation data set is expensive, now I will show you some numbers. This is a very common data set, which is called MS Coco or Microsoft. Okay. This is Microsoft Coco, and to label an image of this dataset, it takes up to 15 minutes. And in this data set, you have 100. Okay, I will switch. Can I remove this one? So, no, both. Okay, so to annotate this data set, you need 15 minutes per image, and you have 100,000 images in this data set. So it takes up to 30,000 hours to annotate the full data set. Another data set I report here is Cityscape. To annotate every image of Cityscape, you need to spend 60 minutes, and the data set has roughly 5,000 images, so it's 5,000 hours. So you can understand what's the cost of annotating such data set. If you want to make your data set, it will be super expensive, that probably you will avoid to do that. And so today I will speak about, can we do something about reducing the annotation cost? So can we train models without full supervision? Can we avoid to have every pixel of the image labeled? And the answer is yes, we have multiple ways to do that. The first one I will present is partial supervision, where we can, instead of having all the classes inside the image annotated, we can have only few ones. So for example, here we have only the horse class, while the person one is not annotated. Then we will have scribbles and points, where basically you don't want to label every pixel of the image, but only few. In this case, you have the all the classes available, but only few pixels. And then finally, we will see image level labels, where image level labels means that you don't have any localization queue, so you don't have pixel-wise annotation. You have just labels on the image. So you know that in the image are present the horse class or the person class, but you don't know where. And the model need to discover that. So in the presentation, I will start from partial annotation, and I will show you an example here of what I mean by partial annotation. So we can have two datasets in this example. Dataset A is made of the person class. So we annotate every person instance on the dataset, but all the other classes are not annotated. So you can see that we can have the dog class, which is not annotated. We can have the horse class, which is not annotated, and the motorbike. This class may be interesting for us, but to spare money, we didn't annotate them. And we have another dataset, which is called animal, where we annotate only the animals, but not the other pixels. So even if we can have humans inside, they are not annotated. And the issue is, can we train a model that is able to predict both person and humans? That's the point of these kind of annotations. And instead of showing you this setting in the offline setting, I will show you what happens when you have first dataset A and then dataset B. That means you have an incremental. Oh. Okay. You have an incremental learning setting. So the dataset A is the person dataset, the dataset B in this example will be the animal. But I will start with another example. So in this example, we have the first dataset is about person as before. Then we learn another class, which is car. And if you see, since every dataset is labeled with only the classes in that step, we have the car class annotated, but all the other classes in the middle row, in the middle column are not annotated. So even if we have car in the background, that's not annotated. And then we learn a new class, which is bike. And again, we have the bike class annotated in the ground truth, but we don't have other classes. And the issues here is that we want to learn new classes over time without forgetting the old ones. And we have only access to new class annotations. So can we manage to remember the old classes, learning the new ones with just new class annotations? The answer is probably yes, but there is an issue that can need to be solved, which is what we call the background shift. So at every incremental step, you see that the background is containing different classes. So in the first step, the background was containing bike and car. In the second step, the background was containing bike and person classes, and in the third one, person and car. So we have this kind of semantic shift of the background class that will lead our model to make mistakes. And to model this background shift, we designed a method which is called modeling background, of course, that actually has two kind of losses. It is an incremental learning setting. So as Umberto presented us before, is based on distillation framework. So we have the old model and the new model. and the old model output is used to constrain the new model. But however, the main issue is here is, can we learn the new classes with using all the annotation availables without forgetting the old one? Because if we learn the new classes using only the ground truth for the old classes will be background probably. And so if we just train a network on this kind of annotation, we will forget what we learned before. So that's an example using only the cross-entropy loss. On the green pixel, you can see what happens when you have the annotation. So very easily, the probability of the bike will be pushed up and all the other probabilities will be pushed down because you want to maximize that probability. You have the ground truth. But what happens on the red pixel is if you use the background as the true label, you will push up the background class and you will push down all the other classes, even if the actual object inside the image is person for that pixel, for the red dot. And so cross-entropy loss will not work in this setting. And we need to find alternatives. The first thing that can come to your mind is let's use pseudo labels. So we can get the model prediction at the current step of PO step, and we can use that as a ground truth. So we can get this kind of output. Gray one is car, the pink one is person, and we can use that on the red pixel to as a target for the cross entropy. So the person will be pushed up, all the other will be pushed down, and that's fine. If the model is good, everything will be good. But what happens if the model is wrong? So if we have a model prediction like this, where the person is predicted as a car, your model will fail. So you will push up the probability of the car class on the pixels, and instead the person will be pushed down. So you have this kind of shift where your model will forget the person and will predict car or background, whatever it predicts. And so can we do better than pseudo labels? Yeah. It turns out that we can do something more theoretical or more practical, I don't know, but it's can we make assumption on the background class, on the background pixels or not annotated pixels? Yes, we can. And because we know that inside the background pixels, there are the classes we learned before. There may be the classes we learned before. So we know that in this image, for example, there can be person, there can be car or background, or all the other classes we learned before. And so we can say, okay, instead of maximizing just one probability, we can make the sum of the probabilities of the classes that can appear in the background and push them up all together. So if the model is confident on some class, that class will be pushed more than the others. If the model is not confident on any class, they will push up all together. And so we are not destroying the confidence, and we are not destroying the what the model has learned before. We are not pushing for a single class that may be wrong. And that's the main finding of this paper. In the same spirit, we designed a distillation loss that follow the same strategy. I will not enter in the details, so I can present you other works, but that's the main idea is that it is the same. So instead of having ground truth, we have the probabilities of the old model. And these are some examples of the qualitative results. You can see that the MIB column is our model, and we were able to get very good predictions for all the classes inside the model. I just mentioned that this same strategy can be extended to other settings, like for object detection. We present this paper at CVPR 22 as a workshop, where we applied the same losses basically to object detection, and we found that it was working. So this is a general way to approach the problem of modeling the background or modeling these kind of partial annotations. And the next step is to see what can we do on partial and scribble, on point and scribble annotations. And it turns out, that's a spoiler, that we can use the same loss as before, but it was a spoiler, sorry. So what are points and scribbles? I mentioned that before. You have only a few pixels annotated in the image, so in form of points or just drawings. And so, but differently from before, you have all the classes annotated. So we don't have issues of having just one class or not all the classes. We have all the classes annotated. And what can we do to learn a semantic segmentation model, since we don't have clear boundaries of the object, and so it can be hard. Well, the simplest solution is to use the partial cross-entropy loss, which means that we are only using the labeled pixels, and we hope that the model is able to generalize to all the pixels in the image. And it works pretty well. The model is kind of good to recognizing objects, but of course the shape will not be perfect. And having realized these previous models said, okay, since the model is not good in determining the shapes of the object, let's use a saliency estimator, which is a model that is able to segment the foreground objects that's trained on another dataset. And let's see if this kind of saliency estimator is able to get the right shape. It turns out that it's kind of it's able to do that, but you need to have another dataset that should be annotated. Even if it's not annotated with classes, you should anyway have a dataset annotated with kind of foreground versus background pixels. And that can be noisy. The third solution is to add loss of consistency, so regularization losses, where you can say, okay, we have pixels that are very close and have a similar color, so probably they are of the same class. They are not different classes. But we did something else, which is exploiting the unlabeled pixels. So as previous work, we started from partial cross-entropy loss, where we have the labels, we use them for the cross-entropy. And so we maximize the probabilities of the ground truth. And we say, okay, what can we do on the other pixels? Can we make assumption on them? Yes, we can, as before, because we know which are the classes inside the image. We know every class inside the image, and we don't just know where they are. So we say, okay, on the unlabeled pixels, we can just maximize the probability of the classes that appears in the image. So we can maximize, in this case, the probability of car, the probability of person, the probability of bike. And we can sum these probabilities. And that's it. That's super simple, but we show that it's working pretty well. So on Pascal Vogue, we compare with some baselines, and these baselines are based on image level labels or image level label plus partial cross entropy, image level label plus partial cross entropy plus what's object is a saliency estimator. And we show that our model is able to outperform them even without any saliency estimation or external data. Yeah, that one. We also show that on AD20K, even if it's very hard on this dataset because you have 150 classes and every pixel is very hard to label, we can show that we were able to outperform the previous methods and also as likely the partial cross entropy. So we can give an improvement on the very baseline. And finally, we show that on scribbles, where we compare with, of course, the partial cross entropy, which was very close to the full supervision, and also to other methods that try to use some regularization in the form of if pixels are similar or not. And we show that we are able to get very close to them without making any assumptions. So our method is general, and we're making a model which is close as performances. Yeah, that one. Okay, and now I will start with the final part of the talk, which is about image level labels. So image level labels, of course, are the cheapest form of annotation you can have. But of course, it's harder to learn a model. The goal is to segment n classes, of course, given all the image level annotations. And an example here is that you have an image representing some classes, in this case, cow, person, car, and motorbike. And the label is just an array, which means which gives you the information of which class is inside and which class is not in the image. And you want a model able to predict this. So you can see that it's super hard to train a model without any localization cube, because you need to associate every pixel to a label, even if you don't know where it is, because they don't provide any localization cube. And what's the idea of the main works that are out now? First, you need to train a model for multi-class classification. So you want to train a standard image classification model that instead of predicting only one class, it's able to predict multiple classes. It's easy. and then use this model to produce pseudo labels, which means that you give a first rough estimate of what the model thinks, where the model thinks are the objects. And then you train a downstream segmentation model with this kind of annotation. So you have two steps typically. The first one is producing the pseudo labels, and the second one is to training the final segmentation model. Here I show an example of which kind of pseudo label we can get in this way. You can see that they are very coarse, so you don't have the right shape of the object. You just have a kind of localization that is good, but it's not enough. In fact, what the current rated works are doing, they are focusing on multi-class classification. They are focusing on adding loss to the multi-class classification, or producing better pseudo labels by means of some refinement step. But I will enter in the detail of this kind of framework. Oh yeah, this is the pseudo label of some refined method. So you can see that here the pseudo label changed, and it's kind of better to recognize the shape. And actually, this is a real pseudo label I get from some method. This has been realized with single stage, which is a CVPR20 paper. So I was mentioning that there is this kind of two-stage framework that first you need to train a model for multi-class classification, and then you extract the pseudo labels. So how can you do that? First of all, use a fully convolutional network that is able to obtain classification scores. Think of that as a common resonant used for image classification, where you remove the pooling on the last layer. So you remove the pooling, you get the classifier on every pixels, and it's done. So you can have just a classification score which is spatial. So you can have for every pixel, of course, on the output resolution, a class. And to train an image level label model, to use the image level labels for your model, you need, of course, to reintroduce the pooling, but you do it after the classification. So in this case, you get the class scores, and then you pool them in a way to make just an array, and you optimize this array to match the classes you have in the image. So in this example, you have cow and probably other classes, and you want to push up the probabilities of those classes and down all the others. Then, when you have this classification score, which is commonly called CAM, class activation maps, you can use them to obtain pseudo labels by means of refinement. So you can use CRF or whatever you want to refine the coarse pseudo labels and obtain the final one that then you can train you can use to train a segmentation model. And this is a bit annoying because you need to train two models. It's expensive, even if you do it without labels for segmentation, which is good, but it's slow. So it's a bit of, it's the drawback of these kind of methods. And so in CVPR20, another method was proposed that is able to train the whole network in just one step. So instead of before that we had two steps, we have just one. So you can see that the figures is very similar, but we don't have the definition of steps. We are still training the model with the multi-label cross-entropy loss, and we aggregating after the classification. But in this setting, in this framework, instead of doing the first step, training the classification model, then a second step, generating pseudo labels, we do that end to end. So we train the model, and while training the model, we generate pseudo labels that are used to train the model again. So if we, 3 minutes left, okay, but I'm close to the end. If you do this, you get pixel cross-entropy loss on the classification score, and if you apply a good refinement, you will be able to extract good pseudo labels to train your model, and in the end, you get a model that is already able to perform segmentation tasks. So you need to train only one model this time. And we applied this framework on incremental learning again. So I will show you again the same application of before, where instead of having the annotation, partial annotation, this time we have only image level annotation. So in this image, we have only the annotation of the cow class, which is a new class, and we don't have the previous annotations. But we assume that we had a model trained on pixel label, on pixel level labels. As I said, we use a single shot single stage setting, sorry. And to do that, we started with the distillation framework where we added a localizer. A localizer is simply a classifier that is able to extract localization for every new class. And the point of the localizer is only this, only to produce a localization map for new classes. This is trained as before. So we aggregate after getting the scores and we train that with the classification loss. To improve the boundaries of the objects, we use a localization prior that is a supervision coming from the old model, which provide guidance of the location of the old classes. So we know where the motorbike, the person, and the car are, so we can exclude those pixels. And also we can use the background prediction as a kind of a saliency estimation. So we can see that if the background prediction is low, probably there's an object inside. After doing this, we get pseudo labels from this, but instead of getting hard pseudo labels, which are super noisy, we found that it's better to smooth them. Smoothing means we get the hard pseudo labels and we interpolate them with the raw probabilities. So if the hard pseudo labels mean that the probability of the class is 1, we mix that with the raw probability, let's say that is 0.5, the final probability that uses target is 0.75. So it's a simple smoothing operation. And then we train our model with a segmentation loss that uses as a target for the new classes, the pseudo labels coming from the localizer, from the old classes, the pseudo labels coming from the old class, the old model, and for the background, the minimum of the two. And everything is trained end to end. So everything is trained in a single step. We learn new classes without forgetting the old ones. We can show that we are able to match the performances of pixel level labeled models. So even without having pixel level labels for the new classes, we are able to match the performances of the old ones. And that was something very mind-blowing for us because we didn't expect these results. We expected to have less results, especially when we added a lot of classes, but we instead showed that we are able to match the performances and even improve them in some cases. These are some examples, and thank you for your attention.
Thank you very much, Fabio, for your presentation. Very interesting, and very interesting to get similar performance with only image level. So if anyone has question, maybe short question before moving to the last speaker.
Thanks very much. What do you do in contexts where you have objects that co-occur all the time? So if you take cityscapes and you've got cars in front of you, you've also got buildings in front of you. Or if you take like a train that's always on a railroad. Are there any good ways of dealing with that kind of thing?
You mean on the last method? Yeah. So the main limitation of this method is that if you train it with only one single class, for example, in the incremental steps, it will fail. And also if you have, the issue is if you don't have any negative example. That means that if you have the new class in every image on the dataset, the model will not be able to localize it because if you have a target which is 1 every time, the model just learned to predict 1. So it will fail to actually localize the class. So in the case of cityscapes, for example, if you're learning the road class is in every image. So it's very hard for the model to really understanding where it is if you don't have negative examples. If you add negative examples, so images without the road class, the model can start to perform well. And the second, I did answer your question. Okay.
Okay, yeah, so thank you for your presentation. My question is, assuming you have a scenario or like a set of data where you have multiple instances of that object. So for example, you have like many cars in a car park, for example, right? So how well is this model, like this method, able to like generate segmentation for each of these, objects?
So for example, this image where you have multiple people inside a single image. Do you mean like this or?
Yeah, but then they're like a lot. And okay, let me give the example of a very busy car park. Okay. Right, so you have cars, then you have buildings, then you have people. Like how well is he able to perform in that kind of scenario?
Yeah, of course, as any data set that has a crowded image, let's say, the performance will start get down. In fact, imagine, sorry, AD20K is a hard data set because you have a lot of these kind of images, or you have multiple instance of person, you have multiple instance of car, and so the things get complicated, even for pixel level annotated data sets. In this case, we didn't push it too much. So the only examples we have is on Coco, where you can have multiple classes. Actually, I think that on Pascal Voc, it's very rare that you have more than 5 or 6 instances of the same class or of multiple classes. I think one of the most crowded images is the one of the ships here. I mean, we probably need to push them a bit farther to see how it performs in crowded images. I think that for semantic segmentation can be easier than other tasks. Like if you need to do instance segmentation will be very hard because you need to discriminate every instance of the image. For semantic segmentation, I think that the model still can get good performances if you have similar examples in the dataset. Because if you have both images that are not so crowded and images that are crowded in the dataset, I think that your model can deal with that, but I have no way to show that.
Okay, thank you.
Thank you very much, Fabio. Let's give him a round of applause again. Thank you very much for being here. So let me introduce Fatma Güney, that is connected online and that will present the last talk. Fatma Güney is an assistant professor at Koç University. I have no idea if I pronounced it correctly, so please correct me after Fatma. And so the university in Istanbul, Turkey, of course. And she has done her PhD in 2017 in the Max Planck Institute. So that's in Germany, and after that she has been doing a postdoc at the VGG group in Oxford, and she will present a work on word prediction model, if I'm correct by memory, and her work focuses on 3D representation learning from video, and generally speaking, geometry estimation with many applications to autonomous driving. So thank you, Fatma, for joining us, and the floor is yours.
Thank you. Thank you very much for the introduction and for the invitation. Hi, everyone. I'm sorry this is the last talk. You must be tired and hungry. I'm going to try to make it quick. And, if you have questions later, we can go into detail. I'm very happy to be here. I wish I could be there. I'm currently in Oxford, visiting Oxford for 3 weeks. I didn't want to put another travel on top of that travel, so that's why I'm attending online. Okay, I'm going to talk about future prediction today. I hope you can all hear me. There is no problem with slides either, I hope, right? Everything is good?
No problem.
Yes.
We hear you very well.
Thank you. Great. Okay. I want to start with a question from Jan Le Kun. So he is asking a very interesting question. How is it that with all the powerful techniques that we have today, all these like huge models, deep learning, right? We cannot get the self-driving vehicle to drive, while a teenager can learn how to drive with 20 hours practice. So, I mean, it might take longer in some cases, like in my case, but this is a very interesting question, right? Basically, the answer that he has in usually his talks or like some podcasts that I listen to is that it's because they have a pretty sophisticated model of the world already. So what does it mean to have a model of the world? Basically, they know the consequences of their actions, right? They know how to anticipate the result of their actions. For example, if you drive off a cliff, it's clear to most humans, I guess, that you will fall, right? So what happens when you do not have a good model of the world? Basically, what we are doing today is when we train, for example, a reinforcement learning agent, we are running off the cliff many times, 1,000 times, until we realize that it's a bad idea, right? So he describes this as one of the main challenges in artificial intelligence today. So that's kind of what I'm going to talk about today, future prediction. So let me try to motivate it a bit more concretely. Why are we interested in future prediction? For example, if you look at this picture, do you think this vehicle on the left is going to move or yield as it's supposed to because it's coming from left and it's our right to go straight, basically? by we, I mean the self-driving vehicle. The situation is ambiguous because even if they are not supposed to do, humans drive in these situations most of the time, right? So if I give you some temporal context, if I show you the video, it becomes clear that the vehicle was indeed yielding and giving the way. So this is just to show you that we need temporal information to predict future. And on top of that, we need to do it with some uncertainty. What do I mean by that? For example, consider this intersection scenario. There's a van coming on the right, and there's a bicycle also approaching. So we don't know if they're going to continue straight or they're going to turn until we see what they do in the end, right? So in these kind of situations at the intersections and so on, we need to predict multiple features with some sort of uncertainty. So first, temporal context. Second, multiple feature predictions with uncertainty. That's what we need. So just like giving you some sort of problem definition, let me tell you how am I going to approach this problem, or what kind of outline I will follow in my talk. Basically, in my research, we are asking the question, what representation space is the best for future prediction? One obvious answer, I guess, is pixels, like when you predict the next frame in a video. And I'm going to introduce a famous baseline called stochastic video generation from 2018, SVG in short. We propose another option, which is motion space. If we explicitly model motion history in addition to appearance history, we show that it might be useful, especially in driving case. And in addition to that, we also show that if we can factorize the motion into different types of motion, such as ego motion and independent motion, it's even better. And last, if you have time, if you are still not super tired, it could be like a unified bird eye view representation. What do I mean by that? As you might know, modern self-driving vehicles are typically equipped with multiple cameras. It's not just a single camera. So instead of doing a future prediction, for example, from each camera, what we could do is we could summarize the information from multiple cameras into this bird eye view representation and do the future prediction in that unified representation. So this kind of started with a work from Wave called FIRE, amazing work, future instance prediction in bird eye view representation. And we build on top of it to extend it, to stretch it to longer time horizons by learning the temporal dynamics a little better. So that's kind of the plan. Let's see how it goes. If I'm out of time, feel free to stop me, or if you have any, I guess questions are in the end, but yeah, I could take questions during the talk as well. Okay. Let's start with stochastic video generation. So this is a very famous work. Everyone tries to compare to them, tries to beat them. This is kind of the baseline in video prediction. So let me introduce it briefly. Okay, we are trying to predict future, and we are trying to do it with some uncertainty by using temporal context as I initially motivated. So how does it look like? We have our car. It's taking pictures from time 1 to time t-1. These are time steps. And now, given this history from time step 1 to time step t-1, our goal is to predict the target frame, what we are going to see at time t, next frame prediction, right? This is the next frame that we will observe in the future, and we are trying to predict it from history, temporal context. So we have access to this target frame during training so that we can learn from it. We can use it to capture the dynamics of the video in our stochastic latent variable ZT. This is like a variational autoencoder. The latent variable Z here carries all the randomness, all the stochastic information about the next frame that we don't have in the history, that we cannot know with a deterministic model, for example, okay? That a deterministic model cannot capture. So I'm going to talk about two models, an inference model and a generative model. Again, if you're familiar with variational autoencoders, it will be very easy because it's just a sequential variational autoencoder at the end of the day. So let me introduce it briefly. So the inference model takes the input frame xt, we call it the target frame, and all the previous frames before xt, from x1 to xt-1, okay? So because of the, and we have the latent variables at each frame, z1, z2, zt. And we show that already this is like x1 is kind of related to z1, x2 is related to z2, and so on. But because of recurrence, each zt not only depends on the current xt, but also all the previous x1 to t minus 1. So from this graphical model, we learn a distribution q phi to sample the z. This is called the inference model or posterior distribution. So this q phi is going to help us to predict the target frame, but it already has access to the target frame xt, right? It could just copy information from that frame. How do we prevent this? As we do in a VAE, we basically use a very low dimensional z, first of all. And second, we enforce or we encourage it to be close to a prior distribution PZ, which is simply a Gaussian in most of the cases. And we minimize the distance between these two distributions with a KL divergence term. So basically what we are trying to do is we are trying to limit the capacity of the latent variable z to force it to focus on the new information, which is not present in the history in the previous frames. So this is the inference model. Similarly, we have a generative model. In the generative model, we are generating x's from z's. And again, as before, each xt depends on current ct and all the previous z1 to t minus 1 through recurrence. In practice, we are just using an LSTM, for example, to model this recurrence relationship. So, so we have a recurrent frame predictor in this case, p theta, which takes previous frames x1 to which takes the previous frames x1 to t minus 1 and samples zt as input and predicts the next frame xt. So this gives us the x hat t, which is our prediction for the next frame, and we try to minimize the difference between the observed xt and the predicted x hat t. Okay, just to make it a bit more concrete, let me show you the architecture. So given frame xt, we use a CNN to encode it typically. Then we have an LSTM, which models the posterior q phi. And this is called the inference model. We sample z from this model. And then given the previous frames, which are encoded with the same CNN, we have the frame predictor, right? And this from the output of the frame predictor LSTM theta, we can decode the target frame. This is the generative model part. Oh, sorry, I just moved too quickly. Okay. So the loss functions, there are two loss functions. The first one is the reconstruction loss between the predicted frame and the target frame. And the KL divergence, which kind of forces the inference model Q to be close to the prior. This prior here can be fixed or learned from the data. Okay, this was the baseline. So now, if you have noticed, we haven't said nothing explicit about motion so far. Every dynamic that is required to predict the next frame in the video, we assume that it can be encoded into latent variable z, right? So what we proposed in our work last year is that what if we explicitly model the motion history as well? Why did we think about this? Because of the data sets that are used, right? The data sets have usually very repetitive motions, like, for example, a person performing some actions like hand waving, walking, running in front of the camera. So these can be very noisy in the pixel space, but if you have some representation of the motion, it's very easy to recognize these repetitive motions. Even for a car driving at the same speed, right? The motion time step after time step is very repetitive. So our idea was to model the motion history to improve the future frame predictions. Basically, in addition to encoding frames, we were also encoding the motion between the frames, which is represented with optical flow. And we were learning two separate distributions representing appearance and motion. As you see here, we are basically factorizing the stochastic latent variable z's as the pixel zp and the flow component zf, right? And then decode the static and dynamic components from the respective one. Just like same as before, but in addition to appearance, we also have this motion component. For the dynamic one, we decode flow, not the frame directly, but if you have the flow and the previous frame, we can basically warp the previous frame according to this predicted flow by using differentiable warping spatial transformer networks to obtain the prediction. So now, what do we have? We have two predictions of the same frame. How do we combine them? We basically ask the network to come up with a mask to combine them in the most optimal way. So this mask MT is kind of creating a weighted combination of the two predictions, pixel prediction and dynamic prediction XF. So how does it look like? Just to give you an idea here, if the mask is close to 1, we are going to rely on the pixel prediction more. If it is 0, we are going to rely on the dynamic prediction more. So we first tested on moving MNIST. Here, as I said, we have two predictions of the same thing. We have a prediction from the appearance component. We have a prediction from the motion component. And we combine them into this final prediction by using the mask that you see at the bottom from but at the row. We can also predict the optical flow, right? Like you see the motion, which is encoded by this false coloring that you see on the top right. So what does it tell us? It basically tells us that we rely on the motion most of the time, and we only rely on the static pixel component when we don't have a reliable motion prediction. When don't we have this reliable motion prediction? When things move, when the pixels become occluded due to digits moving, right? These are motion boundaries around the digits, which flow doesn't work, right? Where the flow doesn't work. That's when we rely on the appearance prediction. In addition to MNIST, we also showed results on KTH. This was interesting because then on KTH, we have this more fine-grained motion of hands, for example, and it can still be handled with optical flow. And you can see the same thing happens here. When hands move, you have these occlusions around the motion boundaries again. And there, you don't have a reliable flow prediction, and the network trusts appearance predictions more when things around the things that move. And these are results on some robot arm data set called Bayer, but not relevant. What was interesting is that even the conditioning frames here that you see here, first 10 frames, don't have any person, for example, in case of KTH. We could still imagine people in the later frames. So this shows the model's capability to capture the dynamics of the data set. Since KTH has these scenes all the time, it can generate samples that are basically close to ground truth, even condition frames are empty. Another interesting thing that we showed is that if we look at the TSNE visualizations of the dynamic versus static latent variables, dynamic was focusing more on the motion. For example, we found that classes, semantic classes with similar motions, such as walking, running, jogging, are clustered closer. They are represented closer in case of the dynamic on the left, as expected, I guess. Okay, lastly, not lastly, I guess secondly, I'm checking the time, but I guess it's still fine, right? I can continue. Okay, any questions at that point? Okay, so
time for us. Take a bit of time to switch on the mic, sorry. I think we'll keep the question for the end, but okay. There is a few minutes remaining, like less than 5 minutes, something like that.
Okay, then I will just show the extension very quickly then.
Great.
Yeah, so when the camera moves, when there is like a camera motion in the background, there is something we do in computer vision. We do molecular depth estimation, right? I'm just gonna skip these slides, but if you are familiar with this work, basically what we are doing is we are predicting depth, and we are using it, we are predicting depth, and we are predicting the motion of the camera, and we are using it basically to reconstruct the next frame and using it as a self-supervision signal. So we thought that we can apply the same idea. I'm just gonna skip these very quickly. Since I don't have time, I'm just going to focus on the main idea, not the details. So we were thinking, can we do the same thing for feature prediction? Can we basically model the camera motion separately from the independent motion of the foreground objects so that we can produce better future predictions. Basically, we've proposed to factorize the scene into static and dynamic components, but this time the static is also moving, and we model the static part based on the scene structure like people do in monocular depth estimation. Predict depth and ego motion to model the background, to model the camera motion in the background. And then dynamic part is just the remaining motion of the dynamic objects. It's basically flow representing the residual motion after modeling the camera motion. So what we are doing is basically we are representing the stochasticity in terms of these factors generating the pixels rather than the pixels themselves. So separate the distributions of motion in the foreground and the background. And there is one more thing, like an interesting idea here is that the changes to the foreground objects are created both by the ego motion and the independent motion of the object itself. So we are basically learning the object motion as residual motion on top of the ego motion by conditioning this dynamic latent variable ZF on the static variable ZP. So foreground motion is conditioned on the background motion. We call it the conditional model. And we show that this model is basically much better suited for future prediction in driving scenes. For example, on Kitty, here you see that the structure and the camera motion can explain the static part of the scene, and the independent motion, which is marked here with the circle of the moving car, is captured by the residual flow. So you can look at the videos here. After the conditioning frames, you can see the predictions of depth, flow, and ego motion separately. Two more interesting cases, also comparisons to other models. Basically, the state of the art at the time was improved VRNN from Facebook in 2019. We couldn't beat improved VRNN, but although our results are similar, it's basically, our model is 40 times faster than the improved VRNN. And this challenging turning case, for example, with the red car is kind of out of distribution on Kitty because there are not many red cars and there are no turning scenarios. It's mostly car moving forward. So only our model here can predict the appearance of the red car, or even further from the conditioning frames in later time steps. We also show the results on cityscapes. Here, the top row shows that like the ego motion prediction can better preserve the lane markings. And in the middle row is again a turning case, which is kind of a rare case. And the bottom one is showing that like the sidewalk and road separation is better preserved with the prediction of the camera motion separately. We also visualize uncertainties. Since we can generate multiple samples from our model, we can basically check the standard deviation across the samples. And we found that our model can pinpoint the uncertainty to foreground objects, whereas in the baseline VRNN, it is more equally distributed across the image. So that's an interesting conclusion because that tells us that stochastic models can focus on the foreground objects because camera motion is generally very straightforward and it's not even different across samples. So there is not much stochasticity there if you can predict the ego motion as we do. That's it, I guess. I'm going to stop here. I'm so sorry that I couldn't show the last part. It's my bad, poor timing. But if you have any questions, feel free to ask.
No problem for the timing. At the end, it's perfect. So you stop perfectly. So among the remaining ones, if there are courageous people that have questions, don't hesitate.
Perfect. Perfect.
Yes, there are questions.
Thank you for your interesting talk. So I have a question. Right now, you are using only 2D information. So would it help to try to integrate some kind of 3D model of the world, even if it is a gross one?
In the last part that I showed, there is 3D. We are predicting depth from monocular sequences. But what is better is, I couldn't talk about it, but doing it in bird eye view representation, like typically you have multiple cameras, right? You have 6 cameras. And when you kind of go to this, first go to 3D and then pull over the height dimension, like project it to the ground by pulling over the height dimension. So this is, I think, what you need. You don't need 3D because you don't need height, but bird eye view is, I think, very good for, it's a very good representation for future prediction. But in the last part that I showed, we were also predicting depth. Here, we are basically, we have this depth predictions from single camera, which are not very good, but
Okay.
thanks for the question.
If there is any other question, yes, there is one. Yeah.
Okay. Thank you so much for your presentation. My question is that you talked about predicting more like future occurrence, right?
Mm-hmm.
So I was wondering what happens if there is a wrong prediction, or would I say a false prediction? Maybe a car is supposed to like move backwards and then it doesn't move. So what is the impact? Would a false prediction have like a severity impact, right? Or it's just minimal?
That's a very good question, actually. And there is really nothing in that direction. So we just, okay. When you look at an autonomous driving stack, there is usually, it starts with perception, right? Given cameras, let me try to detect people and so on. And then there is like prediction, planning, control, which all comes later, right? Even like people focus on each of these modules one by one. There are end-to-end approaches, but it came very later. So the thing that I proposed here is kind of combining the perception and prediction, but there is still no control, no action. Basically, we are not using these predictions for action. We are not learning how to drive or how to act based on these predictions. And that's a very good question. I think these need to be investigated very thoroughly. What happens if you, for example, miss to detect a car, if you predict the motion of the car? I think these questions are very interesting and like a very open research area, much needed research area. Yeah, there is nothing. As I said, it's just combining joint perception and prediction, combining it with control, combining it with planning is to do.
Okay, thank you so much.
Thank you for your question.
All right, thank you very much. I just have one final question.
Yeah.
Given the methods that you showed to us and you explained, you talked about a lot of stochasticity in prediction. So I just want to ask, like, what are the current limitations that you have with the approach and method that you use?
Core limitations of stochasticity, or these models which predict future with stochasticity in general? I guess I can answer both. So one thing that I noticed is that we are trying to do a lot here, right? We are trying to generate millions of pixels and we are trying to model uncertainty overall. I think we should do these things at the object level, because if we can limit ourselves to, for example, stochasticity in objects, right? As I showed in the end, most of the uncertainty comes from foreground objects. I think we can do a lot more interesting things. We can focus our energy on modeling the relations of multiple agents with respect to each other or with respect to the map that we have. Then we can do more interesting things. I think this is one of the biggest limitations. Second, these models are very slow. Usually it takes like 1 second for just one camera, and only one method I think can do it like 100 times faster or 10 times or 100 times faster or so. That's a lot of computation just for predicting the future. So that's like another limitation. Third limitation is, you already see on the slide, the results are not amazing, right? Like when you try to predict 30 frames, it becomes very blurry. You lose foreground objects. So long-term prediction, long-term dynamics are still an open research question. I can continue actually. It can, for example, never predict someone jumping in front of the vehicle because there is nothing like that on the data sets that are curated. So there is nothing interesting happening. You cannot predict weird animals jumping in front of you as you would expect maybe from a future prediction model. So there is a lot of work to do.
Thank you.
Thank you for the question.
Great. I have an additional question, by the way. I haven't worked much personally with optical flow, but quite some work still. And like very practical question is when we work with autonomous driving and especially ego motion in autonomous driving, we have all these problems, for example, of cars driving the exact same speed, which create all the problem of ego motion. And linking that to that very practical aspect, do you think there would be any interest to inject some kind of semantics information? Could be supervised, but could be also weak supervised or even unsupervised, but to inject that semantics into the residual flow estimation, for example?
Yeah, I actually find this like it's a two-way street. So the motion and semantics are quite related. I think you can use semantics for motion or motion for semantics, but a more fruitful way of doing that is joint semantics and motion, I think, and unsupervised, of course. Labeling semantics is a very painful thing to do. I think motion can help a lot with discovering multiple objects. Things moving together are grouped together, the Gestalt principle, right? Like, but that's a great question. I think there is a lot to do in that aspect as well, because right now what people are doing when they do self-supervised motion grouping stuff, they're just focusing on videos where there is only a single object at the center, right? They're just trying to do foreground background segmentation. But motion is especially useful when you have multiple objects, especially useful grouping cluttered scenes, like multiple things moving together and so on. I think it's a very interesting and exciting direction, but I really don't like relying on pixel level semantic labels. That's going to be limited. Whatever you do, right? It's not going to be more than 10,000, tens of thousands, I guess. It's never going to be million, probably. I don't know what companies do. Maybe they have millions of semantic segmentation maps, but yeah.
I think that's a great word to end, because you're highlighting the problem of the need of annotation and the fact that we don't want to have too many supervision. So that's perfect for this workshop. So let's give a round of applause to Fatma again.
Thank you. Thank you, everyone.
Thank you very much, Fatma, for this presentation and for closing the workshop. And just to say to everyone that stayed up to the last bit of the workshop, thank you very much. I hope this has also convinced you to come a bit in the field of computer vision. Again, I know that NLP is super popular here. So come here, and also like, let's push towards like removing the supervision, and let's go towards that direction. We need fresh blood, I think, here. We need you, and I need you personally. So thank you very much, all of you. And again, the recording will be live in a few days. Have a good day. Thanks.
Bye.
Bye.